Hello, and thank you for joining Night Cosmos Sleep. Every day, countless particles of dust and fragments of rock from space race toward Earth at speeds high enough to produce violent impacts. So why do most of them never reach the ground? What causes objects traveling at tens of kilometers per second to leave behind only a brief streak of light before disappearing? The answer lies within the very thin layer of air surrounding our planet. Seen from space, the atmosphere appears as little more than a delicate blue outline. It has no solid surface, and it cannot push an incoming object back the way a wall would. Yet when a fragment of rock begins its descent, this layer of gas can strip away nearly all of its speed and mass within only a few seconds. The air in front of the object is compressed, the temperature rises sharply, and the surface of the rock begins to melt and peel away. Cracks inside it spread wider, causing the object to break into smaller pieces. The light we call a meteor is the visible trace of a cosmic object being transformed by the atmosphere. But how far can this shield protect Earth? Why can a tiny grain of dust disappear completely, while a larger mass of rock may explode in the atmosphere or continue falling all the way to the ground? Tonight, we will follow the journey of a fragment of rock from space and observe how the nearly invisible layer of air around Earth transforms speed into heat, light, and tiny particles of dust. Along the way, a shield that appears almost impossibly fragile will slowly reveal itself, together with both its remarkable strength and its limits. Beyond the outer edge of the atmosphere, the fragment of rock is still moving through almost complete silence. It does not glow, it leaves no long trail behind it, and it appears no more remarkable than the countless pieces of matter traveling around the sundae. If we could place it in the palm of a hand, we might see only a dark, irregular stone marked by fractures that formed long ago. While it remains in space, a small piece of material like this is usually called a meteoroid. Put simply, a meteoroid is a natural object much smaller than a typical asteroid, moving outside the atmosphere of a planet. It may be as small as a grain of dust, as large as a pebble, or reach the size of a substantial boulder. The word meteoroid does not tell us whether the object is dangerous or harmless, nor does it reveal how the fragment will end its journey. The term mainly describes where it exists, beyond the atmosphere, in space, where there is almost no air to slow it down. In that environment, the rock may travel for thousands, millions, or even longer periods with almost no change. It is not worn down by wind as rocks are on Earth. It is not exposed to rain or smoothed by flowing water. Marks on its surface may survive for an immense span of time, like a small record carrying the history of the place to which it once belonged. But the rock's orbit has now brought it close to Earth. Ahead of it is no longer nearly empty space. Surrounding the planet is a vast region of gas, extremely thin at its outer edge and gradually becoming denser closer to the surface. At first, only a few gas molecules strike the rock. These collisions are still too rare to cause any obvious change. The object continues downward with nearly all the speed it carried through space. But as it travels deeper, the number of air molecules hitting its leading surface rises very quickly. The air cannot gently move aside in time. It is compressed in front of the rock, which is traveling many times faster than the speed of sound. A region of compressed and intensely heated gas begins to form. Molecules are broken apart, atoms gain energy, and material on the rock's surface is gradually heated and stripped away. This is also the moment when a streak of light appears high above. From the ground, an observer may see a brief line of light cross the sky and quickly disappear. This glowing phenomenon is called a meteor, commonly known in Vietnamese as a shooting star. There is a small but important distinction here. A meteor is not exactly the name of the rock itself. It is the name of the luminous event produced when material from space passes through the atmosphere. The object is still present inside or just ahead of the glowing region, but what we see is far larger than the object itself. A particle may be no larger than a grain of sand, while the luminous trail around it can extend for kilometers. The observer does not clearly see the tiny particle. What they see is heated air, excited atoms, and material stripped from the object's surface and mixed into the flow behind it. When atoms gain energy through violent collisions, they can emit light. Material from the rock is also eroded away, forming vapor and tiny particles that make the glowing trail more visible. A meteor is therefore not simply a rock burning like a piece of coal in a flame. In many cases, there is little or no chemical burning in the familiar sense. The light appears mainly because the object's speed compresses, heats, and ionizes the air, while also removing material from its surface. What glows is an entire region of hot gas mixed with stripped material, not only the rock at its center. The phrase shooting star can make it seem as though a real star is falling. But the stars we see are so far from Earth that their light may travel through space for years or even thousands of years before reaching our eyes. They do not fall through Earth's atmosphere. The brief streak we call a shooting star is usually created by an object vastly smaller, traveling through the atmosphere at an altitude of tens of kilometers. It is closer to us than any star, yet so much smaller that the comparison is almost meaningless. The familiar name preserves only the feeling people once had when they saw a line of light appear among the stars and suddenly vanish. For most meteoroids, that glowing trail is also the final sign of their journey. The object continues losing mass, breaks into smaller pieces, or turns into vapor before it can approach the ground. By the time the light disappears, the original material may no longer exist in the form of a stone. Sometimes, however, the original fragment is large enough, dense enough, or structurally strong enough for part of it to survive. After being eroded and slowed, the remaining piece is no longer traveling at cosmic velocity. It falls more slowly, is pushed off course by the wind, and eventually reaches land, ice, ocean, or some other surface on Earth. Only when that surviving material actually reaches the ground is it called a meteorite. A meteorite displayed in a museum, studied in a laboratory, or held by a researcher is what remains after the entire passage through the atmosphere. Its outer surface may have been altered by heat and covered by a very thin melted crust, while the interior can still preserve ancient material from before Earth had fully formed. The same journey can therefore be described using 3 different names. While the piece of material is still moving through space, it is a meteoroid. When it enters the atmosphere and produces light, the phenomenon we see is a meteor. If part of it survives and reaches the ground, that surviving piece becomes a meteorite. Not every journey, however, passes through all 3 names. Countless meteoroids produce meteors and then disappear completely. No fragment large enough remains to become a meteorite. Other particles are so small that they slow very gently high in the atmosphere and may settle as microscopic dust without producing an easily visible streak of light. Size clearly influences the outcome, but it is not the only factor. A small, dense, metal-rich object may survive differently from a larger body that is porous, fragile, and filled with fractures. Speed, entry, angle, shape, composition, and internal strength all help determine whether the object vanishes high above, breaks into many pieces, or leaves a small fragment on the ground. The 3 names therefore do more than distinguish scientific terms. They mark 3 very different stages in an encounter between cosmic material and Earth. Silence in space, a brief moment of light within the atmosphere, and the rare surviving remnant that human hands may eventually touch. The name of the rock is now clear. But before it entered an orbit leading toward Earth, it belonged somewhere else. The minerals inside it, the fractures across its surface, and its chemical composition all show that it did not simply appear in empty space. Long before this encounter, it was once part of a larger world. Long before it was called a meteoroid, and before its orbit carried it toward Earth, this fragment of rock was not an isolated object. It once rested within a much larger body, held tightly among layers of stone that had formed during the earliest days of the solar system. Most small pieces of rock, moving through space, did not simply appear on their own. They are often the result of collisions between asteroids, small celestial bodies left over from the era when the planets were still forming. Some collisions only chip a few fragments from the surface. More powerful impacts can produce countless pieces of many different sizes, from extremely fine dust to large blocks capable of surviving for millions of years. In the space between the planets, a collision does not necessarily produce an explosion like the ones we usually imagine. There is no air to carry sound. There is only rock striking rock at tremendous speed, a pressure wave traveling through the material, fractures spreading wider, and a cloud of debris silently dispersing in many directions. Then stillness quickly returns, while each fragment begins following an orbit of its own. The rock we are following may once have rested deep inside an asteroid like this. For an immense span of time, it was covered by outer layers of material and never exposed directly to space. Its mineral composition and internal structure remained almost perfectly preserved, like a sealed record from a time when the solar system was still very young. Then another object crossed its path at exactly the right point in orbit. The encounter lasted only an instant, but it was powerful enough to change everything. The asteroid's outer surface was crushed, blocks of stone were thrown outward, and the fragment that had once rested quietly inside was released into space for the first time. From that moment on, it no longer traveled with its parent body. It followed a new path around the sun, sometimes crossing relatively empty regions, and sometimes passing close to other asteroids. It had no predetermined destination. Its orbit continued to change under the influence of many very small forces, accumulating gradually over time. The gravity of the planets is one of the most important of those influences. When the rock passes near a large planet, even at a great distance, its path can still be pulled slightly off course. A single change may be tiny, almost impossible to notice over one orbit, but after thousands or millions of years, those deviations can carry the object into a completely different region of the solar system. Jupiter, with far more mass than any of the other planets, can strongly influence the motion of objects within and around the asteroid belt. Repeated gravitational resonances can gradually stretch a fragment's orbit, drawing it away from its familiar region and into the area near Earth's orbit. But gravity is not the only influence. Sunlight, although it seems to have no weight, can still alter the motion of a small object. The rock's surface absorbs light, becomes warm, and then radiates heat back into space. If one side is warmer than the other, the released heat is not perfectly balanced, creating an extremely weak push. Over a day or even a year, that force is almost insignificant. But the rock may continue orbiting the sun for an extraordinarily long time. The tiny push repeats on one orbit after another, slowly shifting its path. An object that once remained in the asteroid belt may gradually move into a region where its orbit begins to cross those of the inner planets. Not every piece of material that approaches Earth comes from an asteroid. Another source lies within comets, bodies rich in ice and dust that often follow long orbits around the sunday. As a comet enters a warmer region, ice on its surface begins turning into gas, releasing dust and small rock particles that had been trapped inside. Those particles do not immediately disappear. They continue moving along the comet's orbit, forming an extended stream of material through space. When Earth passes through one of these dust streams, large numbers of tiny particles enter the atmosphere over a relatively short period. From the ground, they appear as the familiar displays known as meteor showers. Most of the material within cometary dust streams is extremely small and porous. These particles may survive for a long time in space, but when they encounter the atmosphere, their fragile structure causes them to heat, erode, and disappear quickly. Even so, during their brief moment of light, each particle carries part of the story of the body that released it. Some fragments have even more unusual origins. Within collections of meteorites found on Earth, scientists have identified samples that did not come from asteroids at all, but were once part of the surfaces of the Moon or Mars. For a rock to leave a world like that, an extremely powerful impact must occur. An asteroid strikes the surface of the Moon, or Mars, at high speed, transfers energy into the ground, and throws some of the material upward. Most fragments fall back, but a small number gain enough speed to overcome the gravity of their parent world and escape into space. From there, they begin orbiting the Sun as independent small bodies. They may complete many orbits before encountering Earth. When one of these fragments passes through the atmosphere and some of its material reaches the ground, it delivers a natural rock sample from a place that is extremely difficult for humans to reach. That origin cannot be determined from the object's outward appearance alone. A rock from Mars may not look very different from many other meteorites. The answer lies in its mineral composition, isotopic ratios, and tiny gas bubbles trapped inside. Some samples contain gases whose composition matches the Martian atmosphere measured by spacecraft, allowing scientists to connect a stone found on Earth with the planet from which it once escaped. Meteorites from the Moon can also be identified by comparing their structure and composition with lunar rocks returned by exploration missions. Through these clues, a small fragment of material can reveal where it once rested, what kinds of rocks surrounded it, and what changes the surface of its parent world experienced. Meteorites are therefore more than rocks that fall from the sky. They are samples delivered naturally to Earth from regions where humans cannot yet easily collect material directly. Some contain matter that has changed very little since the solar system first formed. Others carry traces of heat, pressure, and impacts that occurred on distant worlds. Inside one small stone may be minerals formed before Earth had oceans, before the Moon took on its familiar appearance, and before the planets settled into their present orbits. Those particles once existed within the cloud of gas and dust surrounding the young Sun, then became bound together within the earliest celestial bodies. Over time, many small bodies collided and merged to form the planets, but not all material was used. Some remained as asteroids, comets, and countless smaller fragments. They continued moving between the planets, like unfinished pieces left over from the construction of the solar system. The rock now approaching Earth is part of that remaining material. Its journey has lasted so long that the final few seconds are almost insignificant by comparison. It once belonged to a larger body, was released by an impact, completed countless orbits around the Sun, and slowly changed its path under the influence of gravity and sunlight. For most of that journey, there was no significant resistance to slow it down. Space was nearly empty, allowing the rock to preserve its motion across enormous distances. Its surface remained continuously exposed to solar radiation, high-energy particles, and small collisions, yet its basic form survived. Then, during one particular orbit, its position and Earth's began drawing closer together. A distance that once stretched across millions of kilometers gradually narrowed. The blue planet changed from a tiny point of light into an increasingly distinct sphere, occupying a larger portion of the space ahead. The fragment could not know that it was entering the final stage of its journey. It simply continued along an orbit shaped over millions of years. Below lay oceans, continents, and moving layers of white cloud. Surrounding all of them was a layer of gas so thin that, from that distance, it was almost impossible to see. After traveling so far with almost no resistance, the rock was now moving directly toward that fragile protective layer. And before the first light appeared, it would have to enter a region with no door and no clearly defined surface, yet one that would become increasingly difficult to cross with every kilometer it descended. From the approaching rock's point of view, Earth appears as a bright blue sphere suspended in dark space. The oceans reflect sunlight, bands of white cloud curve around the surface, and along the planet's edge lies an extremely thin blue outline. That outline is the most visible sign of the atmosphere, the layer of matter standing between the rock and the ground below. Compared with the size of Earth, the atmosphere is far thinner than it feels to those of us living inside it. From the ground, the air seems to extend endlessly upward, but when the entire planet is viewed from a distance, That layer of gas looks like little more than a faint glow wrapped around the surface. If Earth were reduced to a sphere small enough to hold in one hand, the part of the atmosphere containing nearly all the air humans breathe would form only a very thin layer around the outside. This apparent fragility creates a remarkable paradox. How can a layer of matter that is almost impossible to see heat, fracture, and destroy most rocks arriving at speeds of tens of kilometers per second? The answer does not lie in a solid surface, but in the way air is distributed around the planet. The atmosphere does not end at one exact altitude. There is no transparent wall for the rock to break through, and no clear moment when space suddenly becomes air. Gas molecules simply become more numerous as the object descends. In the outermost region, they are so widely separated that one molecule may travel a great distance before colliding with another. Closer to Earth, those distances shrink and the number of collisions rises rapidly. The boundary of the atmosphere is therefore more like an extended transition zone than a line. At the greatest heights, light gas particles may still travel along broad paths and sometimes escape into space. Farther down, they gradually become numerous enough to produce the familiar properties of air, pressure, drag, wind, and the ability to carry sound. Scientists divide this region of gas into several layers to make it easier to study. These layers are not separated by distinct surfaces. They are identified mainly by changes in temperature and physical conditions with altitude. For the descending rock, however, the name of each layer matters less than the density of the air it will encounter along the way. Closest to the ground is the troposphere, where nearly all familiar weather takes place. Clouds form, rain falls, and masses of warm and cold air move through this region. It is also the densest part of the atmosphere, because gravity holds most gas molecules close to the planet's surface. Above the troposphere lies the stratosphere. The air here is much thinner, although the lower portion is still dense enough for research balloons and certain aircraft to operate. Temperatures in this layer tend to rise with altitude because ozone absorbs some of the sun's ultraviolet radiation. For people on the ground, the stratosphere is often associated with protecting life from radiation. But to an object arriving from space, it is simply another region along a path where the density of the air continues to increase. Higher still is the mesosphere, an extremely cold region located tens of kilometers above the surface. This is where many meteors become brightly visible and where most small particles are consumed. The air there is still far too thin for humans to breathe, but for a rock traveling at tremendous speed, even that small amount of gas is enough to produce countless collisions every second. A small object may begin interacting with the atmosphere above the mesosphere. In those extremely thin regions, however, the first collisions are not frequent enough to create light visible from the ground. Only after the object descends farther, where the number of gas molecules rises rapidly, do heating, glowing, and erosion become obvious. Above the mesosphere is the thermosphere, where gas particles are extremely sparse but can absorb large amounts of energy from solar radiation. Measured temperatures there can be very high, although an object would not necessarily experience the heat in the same way it would beside a flame. There are simply too few molecules available to transfer a large amount of thermal energy. For the rock, what matters is not the temperature of the surrounding environment before it arrives, but the energy created when it collides with those molecules at enormous speed. Farther out lies the outermost region, where the atmosphere gradually merges with space. Here, the distinction between inside and outside becomes difficult to define. A few hydrogen and helium atoms are still held by Earth's gravity, but they are separated by great distances. The rock can pass through this region with almost no noticeable change in its motion. This explains why the atmospheric shield does not begin working immediately at the outer edge. It does not stop the rock as soon as the object approaches Earth. Instead, it allows the fragment to continue descending through regions where the gas is initially extremely sparse. Only when its path carries it into denser air does the true strength of the shield begin to appear. Most of the atmosphere's mass lies far below the region the rock has just entered, About 99% of the air is held within the lowest 30 kilometers above the surface. This means that the vast region above contains very little matter, while most gas molecules remain concentrated near the oceans, continents, and places where life exists. Gravity is the reason. Earth pulls gas molecules toward the surface, forcing the lower layers to support the weight of all the air above them. Atmospheric pressure is therefore greatest near the ground and decreases rapidly with altitude. A person climbing a high mountain can feel the air becoming thinner, but the change experienced by a rock arriving from space is far more extreme because it crosses tens of kilometers of altitude within only a few seconds. At first, the rock loses almost no speed. A few gas molecules strike its surface and rebound, but there are not enough to cause any significant change. The object continues racing toward the planet, carrying nearly all the kinetic energy stored in its motion. Then, with every kilometer of descent, the number of molecules along its path increases. The collisions no longer occur as isolated events. Air begins gathering in front of the rock because it has too little time to move aside. The object has not yet reached the densest atmospheric layers, but the region around it has already begun to change. This is what allows an extremely thin layer of gas to become such a powerful shield. Air does not need to be as dense as water or as solid as rock when an object moves fast enough. Even thin gas can receive an enormous amount of energy. The number of molecules the rock encounters each second rises so rapidly that its surface begins to experience a continuous assault. This process is especially effective against small particles. They contain relatively little mass to preserve their motion, yet they have a comparatively large surface area in contact with the air. As a result, they lose energy quickly, become hot, and are gradually eroded. Many never descend into the atmospheric layers near the ground. Larger objects can penetrate farther because they carry greater momentum and energy. But even before they are stopped, they must pass through an ever-increasing amount of air. Each layer removes some of their speed, heats the region in front of them, and increases the load placed on their structure. From the ground, most of this process appears only as a short streak of light high in the atmosphere. But within that glowing trail, a rapid transformation is taking place. The thin shield is taking energy from an object that may have traveled freely through space for millions of years and distributing that energy into the surrounding air. The approaching rock is not glowing yet. It has only just passed through the outermost region, where the molecules remain too sparse to produce a visible sign. Below it, the thermosphere, mesosphere, stratosphere, and troposphere follow one another, but no boundary line appears before the object. The shield does not stop the rock at a doorway on the edge of space. It allows the fragment to travel deeper inside, where every kilometer of descent brings more gas molecules into its path. And very soon, those separate collisions will become a violently compressed flow of air building in front of the descending surface. The rock continues racing downward as the distance between it and Earth's surface closes rapidly. At this altitude, air is already present, but it is still too sparse to behave like the continuous substance people experience near the ground. Gas molecules are separated by great distances, and during these first moments, the rock encounters them one at a time along its path. Each collision lasts only a tiny fraction of a second. A gas molecule strikes the surface at tremendous speed, transfers a small amount of energy, and then rebounds or is carried along with the flow. A brief empty interval follows before another molecule arrives. These encounters are still too scattered to produce light bright enough for someone on the ground to see. No sound is heard, and no glowing trail has appeared. From a distance, the rock remains only a small dark point moving toward the planet. Yet its condition has already begun to differ from the long period when it traveled freely through space. For the first time after an immense journey, its motion is being resisted by a material environment, even though that resistance is still extremely weak. People often use an altitude of about 100 kilometers to mark the conventional boundary between the atmosphere and space. This boundary is known as the Kármán line. It is useful in aviation, spaceflight, and regulations involving altitude, but it is not the true outer surface of the atmosphere. No glowing line or membrane appears there, and an object crossing it experiences no sudden impact. Gas molecules still exist above the Kármán line. Below it, the air remains far too thin to resemble conditions near the ground. The boundary simply provides a common reference point for the region where aerodynamic flight gradually gives way to orbital motion. For the entering rock, crossing that altitude causes no distinct change of its own. The encounter with the atmosphere is more like entering a mist that grows steadily thicker. At the outer edge, the mist is almost impossible to notice. Deeper inside, the droplets in that image become more numerous until their presence can no longer be ignored. In the atmosphere, what increases is not moisture, but the number of gas molecules along every section of the rock's path. In a single second, the object may cross a distance that would take an airplane many minutes to travel. At a speed of 20 kilometers per second, it covers a distance comparable to the full length of a large city before 1 second has passed. At greater speeds, it travels much farther still. Natural objects entering Earth's atmosphere usually move at speeds ranging from nearly 11 to about 72 kilometers per second. The lower end is associated with objects drawn in by Earth's gravity from relatively nearby orbits. The upper end can occur when an object moving extremely quickly around the Sun meets Earth on an almost head-on path. Entry speed is therefore not the same for every fragment. An object approaching Earth from behind and traveling in the same general direction may meet the planet at a lower relative speed. One moving in the opposite direction may arrive much faster because Earth's own motion around the Sun adds to the speed of the encounter. The object's earlier orbit determines its approach direction, while Earth's gravity continues accelerating it as it falls deeper into the planet's gravitational field. During the first seconds of entry, however, the rock still retains nearly all of its original speed. The air remains too thin to remove a significant portion of its motion. That velocity is what makes seemingly insignificant collisions so important. A gas molecule has very little mass, but when it meets an object traveling at tens of kilometers per second, the collision carries far more energy than a molecule moving within an ordinary wind. As millions and then billions of collisions begin occurring over extremely short intervals, their effects accumulate quickly. At high altitude, molecules may still strike separate areas of the surface directly. They do not yet behave entirely like a continuous flow of air. But as the rock descends, the distances between molecules shrink. Gas particles disturbed by the collisions begin interacting with one another, creating a complex region of motion in front of and around the object. This transition does not happen in a single instant. There is no specific second before which the rock is completely outside the atmosphere and after which it is suddenly surrounded by air. The collisions simply become more frequent, greater amounts of energy are transferred, and drag increases along a continuous path. The altitude at which an object begins to glow is not fixed either. A very small particle, a dense rock fragment, and a porous object from a comet may respond differently even when entering at similar altitudes. Speed, composition, size, and angle of approach all influence when the energy transferred to the air becomes great enough to produce visible light. Faster objects generally begin glowing at greater altitudes because each collision carries more energy. A porous object may begin releasing material early, allowing a luminous region to form while the atmosphere is still quite thin. In contrast, a dense and durable body may penetrate farther before changes at its surface become obvious. From the ground, observers see only the part of the journey that has become bright enough. The earlier path still unfolds in darkness, even though the rock has already been interacting with the atmosphere for some time. The beginning of a meteor trail is therefore not necessarily the point where the object first entered the air. It is only where the interaction became strong enough for light to travel through tens of kilometers of atmosphere and reach human eyes. Meanwhile, the rock continues descending through an increasing amount of gas, The number of molecules striking its leading surface rises with every second. Molecules that have just collided can no longer escape easily before encountering others. Air begins to gather and compress, producing a region of greater density and pressure than the surrounding environment. This compression is still slight at first, but it increases very quickly. The rock is moving too fast for the air to slide gently around its sides. Molecules ahead of it are forced closer together, collide more often, and absorb energy from the object's motion. Behind the rock, a turbulent wake of gas begins to extend outward. Ahead of it, the environment is no longer made only of isolated molecules arriving one at a time. An aerodynamic structure is forming around the object, even though the entire process is still taking place where the air is far thinner than it is near the ground. The rock has not yet slowed significantly. It still travels tens of kilometers in a single second, but every kilometer ahead contains more air than the kilometer it has just crossed. Drag is increasing, energy is being transferred to the environment more rapidly, and the compressed gas in front of the surface is beginning to change profoundly. Soon, the air will no longer have enough time to move out of the way. It will be forced into a thin region in front of the rock, where the temperature rises until molecules begin breaking apart and atoms gain additional energy. The separate collisions are now merging into a violently compressed flow of gas, and within that heated region, Earth's seemingly invisible shield will begin transforming the rock's speed into heat and light. The region of gas in front of the rock is no longer as sparse as it was only a few seconds ago. Molecules are now being driven into one another continuously, creating a denser and hotter layer of gas around the object's leading edge. The rock is still descending at many times the speed of sound, far too fast for the air to move gently aside and close behind it, the way it does around an ordinary aircraft. Sound travels through air as vibrations pass from one molecule to another. But the rock is moving far faster than those vibrations can spread. The air ahead has not yet had time to receive any warning that the object is approaching before the rock's surface is already upon it. The layers of gas are therefore compressed into a very narrow region. Pressure rises rapidly, and a curved shock wave begins to form in front of the object. This wave does not cling directly to the surface. It stands a short distance ahead of the rock's leading edge, like an invisible dome opening a path through the atmosphere. Ahead of the shock wave, the air remains relatively cold and thin. Immediately behind it, everything has changed. Molecules are forced closer together, move more chaotically, and carry far more energy. The temperature in this region can rise to extreme levels within an extraordinarily short time. This process is often simplified as the rock becoming hot because it rubs against the air. Friction does play a role, especially within the layer of gas moving directly along the surface. But it is not the whole story, nor is it the most important image. What matters more is the mass of gas being violently compressed directly in front of the object. When a gas is squeezed very quickly, the energy of organized motion is converted into the random motion of molecules. In other words, part of the rock's speed is being transferred into the air and appearing as heat. The rock is not carrying a flame with it from space. No fuel is burning the way wood burns in a fireplace or gasoline burns inside an engine. The heat and light are being produced by a different mechanism. The enormous energy of motion is being distributed into the gas surrounding the object. The kinetic energy of an object depends on its mass, but it depends even more strongly on its speed. When velocity doubles, kinetic energy does not merely double, it increases by much more. This is why even a rock that is not especially large can carry a tremendous amount of energy when traveling at tens of kilometers per second. For millions of years in space, that energy remained almost entirely within the object's motion. There was not enough material along its path to remove it. But once the rock meets the atmosphere, the conversion begins very quickly. Every gas molecule pushed aside, every region of air compressed, and every pressure wave spreading outward receives energy from the object's original motion. The gas behind the shock wave becomes so hot that molecules can no longer preserve their familiar structures. An oxygen or nitrogen molecule may be split into separate atoms. If the energy rises further, electrons can be stripped from some atoms, producing a mixture of electrically charged particles. This state is commonly called plasma. It is not a layer of liquid or a flame clinging to the rock, but a region of gas that has absorbed enough energy for some of its atoms and molecules to lose their neutral state. Charged particles move, collide, and exchange energy within an environment that is extremely hot and constantly changing. Some atoms are not fully ionized but are raised into higher energy states. These states do not last long. When the atoms return to lower energy levels, part of that energy is released as light. This is one of the reasons the gas surrounding the rock begins to glow. The light does not come only from the air. Atoms stripped from the rock's surface also enter the hot gas. They collide with other particles, absorb energy, and emit their own characteristic wavelengths. The entire region in front of and behind the object gradually becomes a luminous stream of gas much wider than the rock itself. At the same time, part of the heat from the compressed gas is transferred back toward the surface. Energy reaches the rock in several ways. Hot particles strike it, radiation from the glowing gas shines onto it, and the layer of gas immediately beside the surface is dragged along by the object's motion. Friction still contributes to surface heating. But if we imagine the rock simply rubbing against the air like two solid surfaces grinding together, we miss the most important part. The air is being compressed, heated, and transformed directly in front of the object. That region of gas creates most of the severe thermal environment the rock must pass through. The highest temperature does not necessarily occur directly on the surface. Some of the hottest gas may lie within the narrow region between the shock wave and the rock. This distance is extremely small compared with the full path of entry, yet it is enough to create an intensely heated cushion around the object's leading edge. The shape of the rock influences the way this region develops. A broad, relatively blunt surface can push the shock wave farther outward. A pointed end may concentrate the flow differently. But natural rock fragments rarely have perfect shapes. They spin, vibrate, and change orientation during descent, causing the hot region around them to shift continuously. The surface does not heat evenly either. The side facing directly into the flow experiences the greatest force. Areas sheltered behind it may receive less heat, at least for a short time. As the object rotates, different surfaces move into the heated region one after another, creating a complex thermal history. Even inside the rock, temperature is not uniform. Atmospheric entry happens too quickly for heat to penetrate deeply into the core. The outer layer may melt or vaporize while the interior remains far colder. This differs from the familiar image in movies, where the entire rock becomes a red-hot sphere from the surface all the way through. In reality, the object may carry an extremely hot outer layer around a core that has not had enough time to absorb much heat. If part of it survives and reaches the ground, the interior is not necessarily hot enough to set fire to everything it touches. At this stage, however, the rock is still moving at tremendous speed. The region of gas in front continues absorbing more energy, and pressure rises as the object descends. The increasingly dense atmosphere causes the number of collisions each second to grow rapidly. The shock wave becomes more pronounced, while the wake behind the rock stretches into a glowing turbulent trail. Some of the rock's energy is no longer contained within its motion alone. It has entered the atmosphere, heating the gas, breaking molecules apart, ionizing atoms, and creating pressure waves that spread outward. The shield does not keep that energy in one place. It disperses it across a broader region of air, turning a small object into a phenomenon visible from far away. But this same process is now beginning to alter the surface of the rock itself. Minerals in the outer layers absorb heat faster than the core. Some regions begin to soften, others start to melt, and more volatile components may escape first. The high-speed flow does not allow the molten material to remain on the surface. It strips droplets away and carries them behind the object, where they continue breaking into smaller particles. Some material turns directly into vapor, mixes into the glowing gas, and is swept into the long trail behind. Each layer removed exposes a new surface. That fresh surface is immediately placed in contact with the hot compressed gas ahead, where it is subjected again to intense heat and pressure. The rock begins to lose the shape it preserved throughout its long journey through space. From the ground, this transformation appears only as a moving point of light. Yet within those few brief seconds, the thin atmosphere around Earth is removing energy the rock carried across millions of kilometers. The compressed gas has now become a bright, heated layer surrounding the object's leading edge. The outermost material begins to melt, vaporize, and stream away behind it. From this moment on, the rock is not merely heating up. It is gradually losing its own substance, leaving a brief streak of light within the atmosphere. The first layers of material, torn from the surface, do not disappear immediately. They are swept into the stream of hot gas surrounding the rock, breaking apart into microscopic droplets, metallic vapor, and atoms moving at tremendous speed. At the same time, the air ahead continues to be compressed by the shock wave. A glowing region far larger than the object itself begins to open along its path. From the ground, an observer cannot directly see the small rock hidden inside that light. It may be no larger than a grain of sand, a pea, or a pebble. At an altitude of tens of kilometers, an object that small is far too tiny for the human eye to distinguish. What appears in the sky is the entire region of heated gas, vaporized material, and charged particles moving around it. This is why even a very small particle can produce a streak bright enough to be seen from far away. The size of the light does not directly reflect the size of the object. A fragment only a few millimeters across can activate a glowing region that extends for kilometers, much as the fine tip of a pen can draw a very long line if it moves far enough. Speed is the most important reason for this difference. A grain of sand resting on the ground contains almost no kinetic energy capable of producing light. But when that same particle enters the atmosphere at tens of kilometers per second, it carries a large amount of kinetic energy relative to its size. Within only a few seconds, that energy is transferred into the air and material surrounding its path. The air within the shock wave is compressed and heated. Nitrogen and oxygen molecules collide violently, and some are split into separate atoms. Some atoms lose electrons and become electrically charged particles. This mixture of hot gas containing ions, electrons, and neutral particles can be described simply as plasma. Plasma does not necessarily mean a mass of burning fire. It is a state in which gas has absorbed enough energy that some atoms no longer retain their usual electrically neutral structure. Particles within that region collide constantly, exchange energy, and emit light as they fall from higher energy states back to lower ones. Atoms from the rock itself also take part in this process. As the surface is eroded, elements such as iron, magnesium, sodium, and calcium may enter the hot gas. They absorb energy through collisions and then emit light at characteristic wavelengths when they release some of that energy. But the light of a meteor cannot be explained by one element alone. It is the combined result of many sources appearing together within a region moving at enormous speed. Heated atmospheric gases, atoms from the object, ionized particles, the hot surface, and sometimes newly separated fragments that continue glowing along their own paths. The streak visible to the human eye may therefore be thousands or even millions of times larger than the actual object. A small rock can travel several kilometers in a fraction of a second. Light is continuously produced at new positions, causing the observer to see a long line even though each part of that glowing trail survives only briefly. The effect is somewhat like moving the glowing tip of an incense stick quickly through darkness. The point of light is very small, but the eye may perceive it as an extended line. With a meteor, The scale is far greater because not only the object, but an entire region of gas around it is glowing. When a meteor is described as brighter than a star, this refers only to its apparent brightness as seen by an observer on Earth. The meteor does not actually release more energy than a star. Stars are enormous spheres of gas capable of sustaining their light for millions or billions of years. They appear small and faint only because they are separated from us by distances almost impossible to comprehend. A meteor is much closer. It may appear at an altitude ranging from only a few dozen to more than 100 kilometers, while starlight must travel through space for years before reaching Earth. Because it is so near, a luminous region lasting only a few seconds may still look brighter than many of the stars behind it. Some meteors appear only as a thin silver line and vanish immediately. Others become bright enough to remain clearly visible through city lights. Large or extremely fast objects can produce fireballs bright enough to cast tree shadows, reflect across water, or be recorded even before the sky is fully dark. That brightness depends on several factors at once. Greater mass usually carries more energy, but speed can change the result dramatically. A small object entering very quickly may sometimes create a more striking trail than a larger fragment moving more slowly. The way the object breaks apart also matters, because when many new surfaces are exposed at once, the rate of material loss can suddenly increase and cause the light to flare. The entry angle also affects the shape of the trail. An object descending along a steep path may produce a shorter streak when seen from the ground, even if the event is extremely powerful. An object entering at a shallow angle may travel through a longer path across several atmospheric layers, leaving a broad streak across the sky. Meteor colors can also vary. Some trails appear mostly white or pale yellow, while others carry shades of orange, red, green, or blue. Part of that color comes from atoms within the object, because different elements emit strongly in different regions of the spectrum. Sodium often contributes yellow light, while certain other metallic elements may be associated with green or red tones. However, the color of a meteor should not be used by itself to draw an immediate conclusion about the rock's composition. The atmosphere also glows and contributes color to the overall event. Nitrogen and oxygen in the air can produce different shades depending on temperature, altitude, and the amount of energy they receive. The object's speed changes the degree of ionization. The temperature within the hot gas affects which atoms emit most strongly. Cameras, sensors, and screens also record color differently from the human eye. A highly sensitive camera may reveal colors that a direct observer sees only as a white line. Even viewing conditions make a difference. A streak low near the horizon must pass through a thicker layer of atmosphere before reaching the observer, causing some colors to be absorbed or scattered. Dust, water vapor, and city lights can also alter its appearance. Meteor color is therefore a useful clue, but it usually must be combined with spectroscopy and other measurements before the composition can be identified reliably. After the object passes, the light does not always disappear immediately. A faint trail may remain suspended for several seconds, or even longer in the case of a bright meteor. This is no longer an image of the rock, because the object has moved on or vanished. What remains is a column of ionized gas, together with atoms and microscopic particles left behind along the path. Winds in the upper atmosphere can bend, stretch, or divide this trail into thin strands. From the ground, it may seem to drift slowly among the stars, even though it lies within a region of air tens of kilometers above the surface. By observing the changing form of these trails, researchers can also study winds at altitudes that are difficult to reach. For very small objects, the entire luminous journey may end in less than a second. A particle enters, heats the air, produces light, and is consumed almost completely before an observer has time to understand what has happened. What remains may become metallic vapor or microscopic dust particles that continue drifting through the atmosphere. Larger objects may produce several bursts of light in succession, As material peels away or the internal structure breaks apart, new fragments are exposed to the hot flow and begin glowing as well. The trail may change in intensity, flare briefly, and then fade, as though the object were breathing in short pulses as it falls. But every increase in brightness is usually also a sign that material loss is becoming more intense. The energy that makes the meteor beautiful is the same energy transforming the rock. Most of the glowing atoms in the trailing flow were still inside or on the surface of the object only moments earlier. The luminous streak therefore does more than reveal that a piece of material has entered the atmosphere. It shows Earth's shield removing energy and mass from the object. The longer the glow continues, the more air has been heated and the more material may have been released. The rock we are following still exists inside that luminous region, but it no longer retains its original shape. The dark surface that once moved quietly through space is now continuously heated, softened, and stripped away. Thin layers become vapor, molten droplets, and tiny glowing particles within the stream behind it. The light makes the rock's journey visible from the ground. At the same time, it reveals that the object is losing material very quickly. Beneath the long glowing trail, the surface is being peeled away layer by layer, beginning a process of erosion that may cause the entire rock to disappear within only a few seconds. Inside the luminous trail stretching across the atmosphere, the rock can no longer preserve the surface that traveled with it through millions of years in space. Its outer layers continuously absorb energy from the hot gas ahead of the object. The first minerals begin to soften, melt, vaporize, or be stripped from the surface by the high-speed flow. This rapid loss of material is known as aerodynamic ablation, or simply ablation. It is more than ordinary melting. Some material may briefly become liquid, some may vaporize directly, while other regions are torn away by the force of the gas before they have time to melt completely. Together, these processes cause the rock to grow smaller as it descends. The outermost layer is the first part to endure these conditions. It lies closest to the region where the gas is most intensely compressed and heated, and where countless air molecules continuously strike the surface. Energy enters so quickly that the material has no time to distribute the heat evenly throughout the object. A very thin layer is heated violently, while the deeper material remains largely unchanged. As the outer layer melts, the airflow does not allow it to remain on the surface. Droplets of liquid material are pulled backward, broken into smaller particles, and heated further within the flow. Some glow briefly before becoming vapor. Others cool and turn into microscopic grains of dust that remain suspended in the atmosphere. Atoms that have just left the rock also continue contributing to the luminous trail. They collide with gas molecules, absorb energy, and then emit light as they return to more stable states. Part of a meteor's glow is therefore a visible trace of material being removed from the surface. Every atom appearing in the trail behind the object may have been part of the rock only a tiny fraction of a second earlier. What an observer sees as a beautiful, peaceful line of light high above is actually an object losing small pieces of itself. Ablation does not proceed at a constant rate. When the object enters denser air, the amount of energy transferred to it can rise very quickly. A surface that had been relatively stable may suddenly begin losing much more material. The trail may therefore brighten and fade as the object's speed, altitude, and newly exposed layers change. The rock's composition also affects the way it is eroded. Different minerals do not melt or vaporize at the same temperature. Some components are removed earlier, leaving behind a surface with a different structure from the original. Weak, porous regions or areas filled with fractures may be torn away as small fragments by the airflow. The object's shape also changes continuously. Protruding edges usually experience stronger heating and aerodynamic forces, so they tend to erode more quickly. During the brief entry, sharp corners may gradually become rounded. Each newly exposed surface is then subjected to the same heat, allowing the process to repeat layer after layer. Each layer removed does more than make the rock lighter. It also carries away part of the thermal energy. When melted or vaporized material leaves the surface, the heat used to warm and transform that material departs with it. In this way, ablation can reduce the amount of heat penetrating into the interior. Instead of allowing all the energy to travel toward the core, the outer layer absorbs heat and then breaks away. It behaves like a sacrificial shield, continually carrying heat away from the object. Humans use the same basic principle in some spacecraft heat shields. When a spacecraft returns through the atmosphere, its outer material is designed to heat up, decompose, and peel away in a controlled manner. The lost material carries heat with it, helping protect the structure and interior cabin from the intense environment outside. A natural rock does not possess a deliberately engineered heat shield, yet for a short time, its outer layers can behave according to a similar principle. The surface is continuously removed, and every lost layer slows the transfer of heat deeper into the core. This explains why the entire rock does not necessarily reach the same temperature. The forward surface may become hot enough to melt, while material only a short distance beneath it remains much colder. Heat requires time to travel through matter, but the luminous stage of atmospheric entry usually lasts only a few seconds. The rock may have traveled through the cold of space for an immense period. When it enters the atmosphere, its outer layer changes almost instantly, but the core does not have enough time to heat completely. By the time the object slows and the glowing stage ends, heat from the surface may still not have reached deeply into its center. A meteorite that has just reached the ground is therefore not necessarily glowing red or hot enough to ignite everything around it. The exterior may still be warm, and large objects can sometimes retain considerable heat, but the interior may be far cooler than the familiar images shown in movies suggest. In some cases, the meteorite may even cool during the final stage of its fall. Once it has lost most of its cosmic speed, it no longer produces the powerful region of hot compressed gas that surrounded it earlier. During the remaining descent, it falls under gravity and drag, with enough time to exchange heat with the cold air around it. The difference between the exterior and the core is preserved in many meteorite samples. The surface may carry a thin, dark layer formed when the outside melted and then solidified again. Yet directly beneath that crust, ancient minerals may remain almost perfectly preserved. Ablation does not depend only on heat. Its effectiveness is also closely related to the ratio between the object's surface area and its mass. This is one reason very small particles are often consumed more easily by the atmosphere. A dust particle contains very little mass, and nearly all of its material lies close to the surface. Energy from the air does not need to travel through a thick layer of rock before affecting the interior. A relatively small amount of heat may be enough to warm almost the entire particle. As an object becomes larger, its mass increases faster than its surface area. A large rock contains much more material deep inside, protected from the external environment during the first few seconds. It may preserve its motion and lose its outer layers without being completely destroyed. A small particle, by contrast, has a large area exposed to the air compared with the amount of material it contains. Each unit of mass receives a relatively large amount of energy. Drag also slows it more quickly because it has little inertia to preserve its original speed. Many small particles entering the atmosphere therefore heat up, lose material, and turn into vapor before reaching the lower layers. They leave behind no meteorites that can be collected from the ground. Their remains become metallic atoms, compounds, and extremely fine dust dispersed through the atmosphere. The tiniest particles, however, can meet a different fate. If they are light enough, drag may slow them high in the atmosphere before temperatures rise enough to destroy them completely. They can then settle gradually as micrometeorites, so small that they may blend into the natural dust on Earth's surface. Small size does not therefore always mean complete destruction. The outcome also depends on speed, structure, and the way an object exchanges energy with the air. One tiny particle may be consumed as vapor, while another slows early and survives in nearly its original form. For the rock we are following, Ablation is becoming more intense. It is still large enough to retain part of its original speed, so it continues descending into denser air. Its outer layers are being removed, but the core still survives behind the changing surface. With every passing second, the object becomes slightly lighter. Its shape grows less regular, weak regions are gradually exposed, and fractures inside begin moving closer to the surface. A crack that once lay deep within the stone is now covered by only a thin layer of material. The luminous trail behind it shows that matter is leaving the object, but ablation cannot destroy every incoming body in the same way. If the rock is large enough or strong enough, it may continue downward even after losing a significant part of its mass. Meanwhile, the air ahead is being compressed more intensely. Increasing density causes greater pressure against the front of the rock, while its rear remains within thinner and more turbulent gas. This difference begins placing a new kind of load on the entire structure. During its long journey through space, the rock encountered almost no comparable force. Internal fractures could survive for millions of years without widening significantly. Now they are being pulled, compressed, and shaken by the surrounding flow. Ablation has made the rock smaller, but heat is not the only force transforming it. Pressure ahead continues to rise, while the internal structure begins enduring a load it never experienced in space. If even one weak point expands quickly enough, the rock will no longer remain a single object. The fractures that once lay dormant inside the rock are now beginning to move. In space, they may have survived for millions of years without causing any noticeable change. There was no air pressing against the surface, no stream of gas pulling the object in different directions, and no powerful vibrations traveling continuously through its structure. Even though the rock was not completely intact, it could continue orbiting the sun as a single body. But as it plunges deeper into the atmosphere, the environment around it has changed completely. The leading face must push an increasing amount of air out of its path, while the rear lies within thinner, more turbulent gas. This difference creates a force that passes through the entire object, strongly compressing the front while stretching the regions behind it. This force is often described through dynamic pressure, a quantity that increases as the air becomes denser and rises especially sharply with greater speed. The rock is still traveling at tens of kilometers per second, so even a region of air that remains extremely thin can place a significant load on it. As the object descends, the number of air molecules along its path grows, causing the pressure against its surface to change rapidly within only a few seconds. Outside, the object continues glowing and undergoing ablation. Inside, each small fracture begins to feel the stress. Some cracks are pressed closed, while others widen. Different minerals do not expand and contract in exactly the same way under heat, making the boundaries between them weak points. Collisions that occurred long ago left damage behind, and the atmosphere is now revealing it. Not every small object is a solid block of stone. Some asteroids and their fragments have porous structures filled with empty spaces. Some are made of many smaller rocks resting against one another, held together only by weak gravity and contact between their surfaces. A structure like this is sometimes called a rubble pile, although the pieces within it may vary greatly in size and shape. In space, such a loosely assembled structure can survive. But during atmospheric entry, its different sections do not experience the same forces. The material at the front is slowed first, while the rear continues trying to move at its previous speed. The weak connections between those sections begin losing their ability to hold the entire object together. Even a rock that appears solid has a limit to its strength. Material can withstand only a certain amount of tension, compression, or bending before cracks begin spreading more quickly. Once the aerodynamic load exceeds the strength of the structure, the change can occur almost instantly. A small fracture expands through the stone. It reaches another weak region, changes direction, and continues spreading. Within a tiny fraction of a second, the crack travels from the interior to the surface. The mass of rock that remained together across millions of kilometers can no longer preserve its shape. The rock breaks apart. From the ground, that moment may appear as a sudden bright flare that divides into several smaller streaks. The object that had looked like a single line of light becomes a cluster of glowing fragments separating across the sky. Some pieces remain close together, others move outward to the sides, while the smallest quickly fade and disappear. The increase in brightness does not necessarily mean that the object has suddenly received additional energy from outside. Most of the energy still comes from the motion it already carried. What has changed is the way that energy is being transferred into the atmosphere. When the rock breaks apart, many new surfaces are exposed to the hot airflow at once. Before fragmentation, the interior was protected by the outer layers. Afterward, surfaces that had never directly touched the atmosphere are immediately exposed to compressed, heated gas. Energy enters through more areas, material is ablated more rapidly, and the number of atoms entering the luminous flow rises suddenly. The light may therefore flare for a brief moment before weakening again. Observing instruments can record these changes in brightness as a light curve. Peaks along that curve often mark episodes of intense material loss or fragmentation. An object may flare once and then vanish, or it may experience several successive bursts as larger fragments continue breaking into smaller pieces. The first fragmentation is rarely the end of the process. A large mass divides into several pieces, and each fragment continues to experience aerodynamic pressure. New fractures are exposed, while the material has already been weakened by heat and shock. A newly released fragment may remain intact for only a very short time before breaking apart again. With every stage, the original object gradually becomes a cloud of debris distributed along its path. Larger fragments preserve more of their high speed and continue descending. Smaller particles are slowed more effectively by the atmosphere and quickly lose speed or are consumed as vapor and dust. This is one of the ways the atmosphere weakens an incoming object. While it remains one large mass, the rock contains a great amount of material behind a relatively small frontal area. It can preserve its motion more effectively and pass through a considerable amount of air before slowing noticeably. After it breaks apart, the total surface area of all the fragments increases. More material is exposed to the atmosphere at once, while each fragment retains only part of the original mass. The ratio of surface area to mass therefore becomes greater, allowing drag to act more efficiently on every piece. A large rock can be imagined as a heavy object forcing its way through the air. Once it breaks into hundreds of fragments, there is no longer one large mass driving forward. Each smaller piece must make its own way through the gas, endure its own drag, heat up independently, and lose its own material. This creates a powerful feedback process. Smaller fragments slow more quickly. As they decelerate, they may be pushed away from the original path. Newly exposed surfaces are heated and eroded, making the fragments smaller still. If they continue breaking apart, drag becomes even more effective. Fragmentation, therefore, often helps the atmospheric shield work more efficiently. Instead of having to slow one large mass, the air now interacts with a cloud of smaller fragments that has a much greater combined surface area. Many of those pieces are completely consumed before reaching the lower atmosphere. That does not mean the object's energy has disappeared. Energy is not erased when the rock breaks apart. It is transferred elsewhere and into different forms. Some heats the atmosphere, some produces light, some creates shock waves, and some remains within the motion of the fragments that continue descending. If fragmentation occurs at high altitude, the energy can be transferred into a broad region of the atmosphere before the remaining effects travel toward the ground. The air has more distance over which to weaken the pressure waves and continue slowing the smaller pieces. In many cases, this causes most of the material to disappear without producing any clear consequences below. If the object maintains its structure until a lower altitude and only then breaks apart, its energy may be released closer to the surface. In that case, the light, pressure, and shock waves may affect the region below more strongly, even if most of the rock still does not reach the ground intact. It is therefore not only the total energy that matters, but also the altitude and duration over which that energy is released. The same amount of kinetic energy, spread gradually along a long path, produces a different result from energy transferred into the atmosphere in one brief, concentrated event. The rock we are following has not produced an exceptionally large energy release. It is broken into several pieces, but each one carries only a small fraction of the original mass. Glowing fragments separate behind it, forming a cluster of thin trails before fading one after another. Some of the smallest particles nearly stop within the upper atmosphere. They lose their speed, gradually cool, and begin drifting with the air currents they had previously been cutting through. Larger fragments continue downward, but they are no longer protected inside the original mass. Air now reaches them from several directions. The fragments spin, vibrate, and change orientation as their irregular shapes cause drag to be distributed unevenly across their surfaces. Some pieces break apart further, while others retain their structure long enough to penetrate deeper. Behind them, the luminous trail expands and slowly fades. Atoms that once formed part of the rock mix into the atmosphere. Ahead, the remaining fragments begin experiencing another change. Their speed is no longer being preserved almost completely as it was when they first entered. Each fragment pushes a mass of air forward, transfers momentum into the surrounding environment, and leaves turbulence behind. The immense motion that remained almost unchanged across space is now being removed rapidly. After fragmentation, the smaller pieces are held back far more effectively by the air. Their descent is no longer only a process of heating and losing material. It is becoming an enormous deceleration in which each part of the rock's motion is gradually transferred back into the atmosphere surrounding Earth. When the rock first began entering the atmosphere, its speed was still almost unchanged from the time it had spent in space. In a single second, it could travel tens of kilometers, fast enough to leave an entire large city behind before one breath had ended. But after breaking into several smaller pieces, that motion began to decline noticeably. Each remaining fragment now had to force its own way through the air. Ahead of it, gas molecules were pushed aside, compressed, and drawn into the shock wave. Behind it stretched a turbulent region of gas containing vaporized material, tiny particles, and currents swirling into one another. Every one of these changes required energy, and the only source of that energy was the fragment's original motion. The atmosphere does not stop an object with one sudden pull. It removes speed through countless small collisions occurring continuously. Every gas molecule striking the surface receives a fraction of the object's momentum before being pushed out of the way. One collision means almost nothing, but their number rises rapidly as the fragment descends. The rock pushes the air forward, and the air pushes back. The force opposing the object's motion is called aerodynamic drag. It depends on the density of the air, the object's shape, its exposed surface area, and especially its speed. While the velocity remains extremely high, drag can become powerful enough to alter the motion within only a few seconds. A fast-moving object does more than push aside the molecules directly ahead of it. It also produces shock waves that spread outward, heats a broad region of gas, and leaves turbulence behind. Each of these processes removes more energy. The organized motion of the rock is gradually transformed into heat, light, pressure waves, and chaotic movement within the atmosphere. Momentum is transferred to the air in much the same way. Before the rock passes, gas molecules move randomly around their positions. After the encounter, some of the air has been pushed sideways, some moves in the object's direction, and some becomes caught within swirling currents behind it. The atmosphere has taken on part of the motion the rock once carried. The deceleration does not happen at a steady rate. In the thinner upper atmosphere, the object may travel many kilometers while losing only a small fraction of its speed. But as it descends, every section of its path contains more air. Eventually, drag rises far more quickly than it did only seconds earlier, and the velocity begins to fall sharply. For someone observing from the ground, this stage often occurs during the brightest part of the flight. The rock is still moving extremely fast, but energy is now being transferred into the atmosphere at a tremendous rate. The trail may flare, more fragments may separate, and motion that remained almost perfectly preserved in space begins to be removed piece by piece. The smaller a fragment is, the more easily it can be slowed. After the object breaks apart, each piece has less mass while still presenting a significant area to the airflow. The atmosphere can therefore act on a greater proportion of the material. Small fragments lose speed quickly, while larger and denser pieces retain their motion for longer. The difference can be imagined through two objects with the same shape but different sizes. The larger one contains more mass behind the surface pushing through the air, giving it greater inertia. The smaller object has less mass available to preserve its motion, so drag changes its speed more easily. This is one reason fragmentation allows the atmosphere to consume an incoming body more effectively. As the velocity falls, the compressed region of gas ahead also begins to weaken. The shock wave becomes less intense, less heat is produced, and the glow starts to fade. The fragment is still high above the ground, but it is no longer racing through the atmosphere at cosmic speed. The disappearance of the luminous trail does not necessarily mean the object has been completely destroyed. Some fragments may still exist, but they have slowed to the point where they no longer generate enough heat or ionization to produce visible light. From there, the journey enters another stage, commonly called dark flight. During dark flight, the meteorite fragment no longer appears as a glowing streak. It becomes an ordinary falling object within the atmosphere, pulled downward by gravity and resisted by drag. Its motion now resembles a stone falling from a great height more than an object racing through space. Gravity continues accelerating it toward the surface, but as it falls faster, drag also increases. Eventually, the two effects approach a near balance. Gravity pulls downward, while the air pushes upward with an approximately equal force. At that point, the speed no longer increases significantly. This stable velocity is called terminal velocity. Terminal velocity is not the same for every meteorite fragment. A small, lightweight, irregular piece may be held back quite effectively by the air. A dense, heavy, compact fragment can fall faster. Its orientation, rotation, and the area facing the airflow also cause its speed to change continuously. A flat fragment may catch more air and slow strongly. A rounded or compact mass may pass through the atmosphere more easily. If the object tumbles chaotically, the area facing the flow changes from moment to moment, causing the path to become less straight and stable. Even so, the speed during dark flight is far lower than it was when the object first entered the atmosphere. A fragment that once traveled at tens of kilometers per second may now be moving at only tens or hundreds of meters per second, depending on its size, shape, and mass. That is still fast enough to dent the ground, damage a roof, or cause injury if it strikes something, but it is no longer a hypervelocity impact like those that occur in space. The difference between these two states is enormous. During a hypervelocity collision, an object carries enough kinetic energy to compress, heat, and destroy material almost instantly. Rock and metal can behave almost like fluids under extreme pressure, and a crater may form within a very short time. A small meteorite that has entered dark flight no longer produces those conditions. It reaches the ground as a rapidly falling object, not as a projectile that has preserved its cosmic velocity. Most of its original dangerous energy has already been transferred to the atmosphere through light, heat, shock waves, and turbulence. As the fragment falls, wind begins to affect it more noticeably. While it was moving at tens of kilometers per second, a crosswind could barely alter its path during the few seconds of luminous flight. Once it has slowed, however, the rock remains in the atmosphere longer and can be pushed sideways by moving air. Winds at different altitudes do not necessarily blow in the same direction. A fragment may be carried eastward through one atmospheric layer and then shifted another way as it descends. Smaller pieces are affected more strongly because drag is large relative to their mass. Larger fragments usually preserve more of their original direction and travel farther along the path of motion. The place where a meteorite reaches the ground is therefore not directly beneath the point where the glowing trail disappeared. During dark flight, it may drift sideways for many kilometers. When an object breaks into multiple pieces, the fragments usually fall across an elongated region rather than gathering at one point. Researchers searching for meteorites must combine several kinds of information: the observed flight path, the altitude where the object stopped glowing, the estimated size of the surviving fragments, and atmospheric wind data. Even a small difference in velocity or wind direction can shift the search area considerably. The rock we have been following has now lost almost all the speed it carried from space. Some small portions have become vapor and dust. Other particles were stopped high in the atmosphere. Only a few fragments remain dense enough to continue falling through the darkness. There is no longer a brilliant region of gas around them. No fiery trail stretches behind them. The stones pass quietly through the lower atmospheric layers, turning slowly, shifting slightly with the wind, and continuing to cool as they descend. The atmospheric shield does not need to make every object disappear completely. Simply removing its speed can profoundly change the outcome. An object that could once have released violent energy in an impact has become a small stone falling under the familiar influence of gravity and air. But not every object is slowed in the same way. A porous structure may cause a rock to break apart early and lose speed quickly, while an iron-rich mass retains its motion for longer. A lightweight particle of cometary dust may vanish in the upper atmosphere, while a denser body continues penetrating downward. Entering the same atmosphere, a porous stone, a compact iron mass, and a particle of comet dust can meet entirely different fates. What determines their outcome is not only their size, but also the material, shape, and internal structure they carried from the place where they first formed. Three objects can enter the same atmosphere at nearly the same speed, and yet end their journeys in three completely different ways. A lightweight dust particle may slow high above Earth and then drift quietly downward. A larger stone may create a brief streak of light before disappearing. Meanwhile, a denser and stronger body may penetrate deeply through several atmospheric layers, leaving fragments large enough to reach the ground. Size is often the first thing people mention when trying to predict an object's fate. That makes sense, because a large body usually carries more mass and kinetic energy than a small particle. But size alone cannot provide the answer. Two objects with the same diameter may differ greatly in mass, strength, internal structure, and their ability to endure passage through the atmosphere. At the smallest end of this range are particles of cosmic dust. Some are so tiny that drag slows them while they are still in an extremely thin region of the atmosphere. Because they lose speed early, they no longer produce compressed gas hot enough to melt them completely. Instead of becoming a clearly visible meteor trail, they may settle gradually through the atmospheric layers as microscopic particles and eventually reach the surface as micrometeorites. This outcome may seem to contradict what we have already seen. If small particles heat so easily, how can they survive? The answer is that they also slow down very easily. An extremely small particle has very little inertia, so the atmosphere can remove its speed before enough heat accumulates to destroy all of its material. Once its motion has slowed, the period of intense heating also comes to an end. Slightly larger particles, around the size of grains of sand or pebbles, may create more visible streaks of light. They are large enough to retain their speed for a short time, but they do not contain much material deep inside that can remain protected. Heat and drag act on nearly their entire mass, causing them to undergo ablation very quickly. Many objects in this range glow for a few seconds and then become vapor and dust before reaching the lower atmosphere. As size continues to increase, the object gains more mass with which to preserve its motion. Its outer layers may be stripped away, while the material deeper inside continues to survive. If the structure is strong enough, a larger rock can break into several pieces, with some fragments passing through dark flight before reaching the ground. Meteorites that are eventually found are usually the remains of a long sequence of ablation, fragmentation, and deceleration, rather than intact objects that entered directly from space. For still larger objects, the atmosphere may not have enough time to remove most of their energy gradually. They continue penetrating downward while retaining extremely high speed. When aerodynamic pressure exceeds their structural strength, they may break apart violently and transfer a large amount of energy into the air over a short period. The result is an airburst, where the main danger may come not from the rock striking the ground, but from shock waves, heat, and pressure spreading through the surrounding region. Even so, there is no single diameter that can reliably divide harmless dust, surviving meteorites, and objects capable of producing airbursts. A porous body may break apart earlier than a smaller but denser object. A fast-moving fragment may release more energy than a larger body traveling more slowly. Entry angle, shape, and the location of internal fractures can also change the outcome completely. Material composition is therefore just as important as size. Fragments originating from comets often contain large amounts of lightweight material, dust, and empty space. They may resemble loosely assembled collections rather than solid blocks of stone. When they encounter rapidly increasing pressure in the atmosphere, these structures break apart easily, causing the body to separate into countless small particles and be consumed at high altitude. Stony meteorites are more common among the samples found on Earth. They are composed mainly of silicate minerals, but they are not always uniform masses. Their interiors may contain fractures formed by earlier impacts, regions of different strength, or weak boundaries between minerals. A stone that looks solid from the outside can still break apart quickly when those weak points are exposed to aerodynamic pressure. Iron-rich meteorites are generally denser and stronger. A mass of iron and nickel may preserve its shape for longer during atmospheric entry, while also containing more mass within the same volume than a porous rock. It is still heated and ablated intensely, but it may penetrate farther before slowing or fragmenting. This does not mean an iron object will always reach the surface intact. If it is small, it can still be slowed, melted, or stripped of most of its mass. If its structure contains weak regions, it may still break apart. Stronger material only changes the probability and depth of survival. It does not make the object immune to the atmosphere. Between the stony and iron groups are stony iron meteorites, which contain both silicate minerals and metal. Their internal structures can be remarkably beautiful when cut and polished, but in the atmosphere, they still face the same fundamental processes: compressed gas, energy transferred into the surface, material stripped away, and drag reducing their speed. Density also creates a significant difference. Two objects with the same outer dimensions may have very different masses if one is solid, while the other contains many empty spaces. The denser body carries more momentum and is harder to slow. A porous body has less material behind each unit of exposed surface area, allowing drag to alter its motion more easily. Porosity affects more than mass. It also changes the way pressure travels through the object. Hot gas may enter openings, exposing internal regions to heat and force from several directions. Small blocks resting against one another may separate, causing fragmentation to begin earlier than it would within a solid body. Shape also helps determine how an object moves through the air. A broad, flat body presents a large area to the airflow and is therefore easier to slow. A compact and dense object may preserve its speed for longer, but natural fragments often tumble chaotically, causing the forward-facing surface to change continuously. Drag, heat, and pressure are therefore distributed unevenly throughout the flight. An unbalanced object may also vibrate, flip, or move away from its original direction. These motions cause loads to shift across different regions of its structure. A fracture that was previously stable may suddenly experience strong tension. A protruding section may erode quickly, causing the object's shape and motion to change again. Entry speed is especially important because kinetic energy rises very strongly with velocity. An object moving only somewhat faster may carry significantly more energy. It compresses the atmosphere more intensely, begins glowing at a greater altitude, and experiences stronger aerodynamic loads. Two fragments made of the same material and having the same size may therefore meet very different outcomes if they enter at different speeds. An object's strength cannot be inferred from its composition alone. Two stony meteorites may contain similar minerals, yet one may have been struck repeatedly in the past and contain countless microscopic fractures, while the other is more solid. When atmospheric pressure acts on their surfaces, the more heavily damaged object will usually fragment earlier. Size, therefore, reveals only part of an object's potential fate. To understand what will happen, we must consider the entire combination of mass, density, porosity, composition, strength, shape, speed, and internal structure. None of these factors acts completely alone. A very small dust particle may slow before melting. A pebble may glow and then disappear. A larger rock may break apart and create a meteorite-strewn field. A porous body may fragment high in the atmosphere, while an iron-rich object of the same size penetrates farther. With very large objects, too much kinetic energy remains for the atmosphere to remove completely before they approach the ground. The atmospheric shield therefore does not impose the same outcome on everything that enters it. It responds to what each object carries with it. A fragile structure is torn apart. A small particle is slowed. A dense body gradually loses its outer layers, but continues downward. Its fate takes shape second by second as the properties of the object meet the steadily increasing density of the air. The rock we have been following has already lost most of its mass and speed. Its more porous sections disappeared first, while a few denser fragments continued falling. But even when their size, material, and structure are known, one more factor can lengthen or shorten the entire encounter. An object descending almost vertically will travel through the atmosphere along a very different path from one that only skims the upper layers. The angle at which the rock meets Earth will determine how much air it must cross, the altitude at which it loses energy, and whether its journey lasts only a few seconds or extends across a far greater distance. A rock may carry the same mass, the same composition, and nearly the same speed, yet even a slight change in the angle of its path can make its encounter with the atmosphere unfold very differently. What matters is not only how fast the object is moving, but how much air it must cross before reaching the lower layers. An object descending almost directly toward the ground follows a relatively short path through the atmosphere. It moves quickly from extremely thin gas into regions of greater density. Within only a few seconds, the number of molecules striking its surface rises sharply, aerodynamic pressure increases, and more energy is transferred into the air at lower altitudes. A steep path does not mean the object escapes ablation. It still produces a shock wave, still becomes intensely heated, and may still fragment. But because it spends less distance within the upper atmospheric layers, the air has less time to remove its speed before it penetrates deeply. A sufficiently large and durable body can therefore carry more energy closer to the surface. If the object breaks apart at this stage, its energy may be released within a relatively small region. Pressure waves also have less distance over which to weaken before reaching the ground. This is why the altitude of fragmentation can be just as important as the total energy the object carries. An object entering at a shallow angle experiences a much longer journey. Instead of plunging rapidly downward through the atmospheric layers, it travels almost parallel to Earth's surface for a period of time. Even while remaining at high altitude, it must pass through a far longer column of air. The atmosphere can be imagined as a thin layer of material wrapped around a sphere. Traveling straight through that layer is the shortest route. But when an object moves diagonally, It remains inside the gas longer before it can descend or escape. Every additional kilometer brings more collisions, greater drag, and more time for the surface to undergo ablation. A shallow trajectory can therefore allow the atmosphere to slow an object more effectively. The density rises more gradually along its path, but the object remains exposed for a longer time. Its surface may lose material across a wide distance, while its luminous trail stretches through a large region of the sky. From the ground, a shallow meteor may appear as an extremely long streak, almost gliding sideways near the horizon. This does not necessarily mean it is larger than an object that creates a shorter trail. The longer line may simply show that the meteor is crossing the atmosphere along a more inclined path. The shape seen by an observer also depends on viewing position. A path that is actually very long may appear short if the object is traveling almost directly toward the viewer. In contrast, when the motion passes sideways across the line of sight, the full luminous trail may extend across a large part of the sky. Entry angle also changes where energy is transferred into the atmosphere. A steep path may carry energy deep downward within a short time. A shallow path usually spreads that energy across a longer distance and at greater altitude. Instead of being concentrated near one point, the light, heat, and pressure waves are distributed over a broader region. But a shallow angle is not always safer. If the object is very large, it may still retain a great deal of kinetic energy even after traveling through a long section of atmosphere. A nearly horizontal path may also spread its effects across a wider area. Entry angle only becomes meaningful when considered together with size, velocity, composition, and structural strength. A small, porous rock entering at a shallow angle is often ablated very effectively. It has more time to lose material before reaching dense air. A denser metallic body may continue preserving its speed even as its surface heats, and is stripped away layer by layer. Initial velocity also changes the way entry angle affects an object. A very fast rock transfers more energy in every collision, allowing it to begin glowing and losing material while the atmosphere is still thin. A slower body may penetrate farther before its luminous trail becomes clearly visible. Beyond ordinary steep and shallow trajectories, there is a rarer kind of passage. Sometimes an object does not plunge deeply into the atmosphere at all. Instead, it touches the outer portion of the gas layer, follows the curvature of Earth for a time, and then continues away. Events like these are commonly called Earth-grazing meteors. During such an encounter, the object enters at an extremely shallow angle. It begins glowing as it collides with the upper atmosphere, leaving a trail that may extend across a tremendous distance. But instead of continuing downward, the curvature of its path gradually carries it farther from the surface. The atmosphere does not capture the entire object. Some material may be ablated, and smaller fragments may separate and disappear, but the surviving portion retains enough speed to return to space. From the ground, the glow gradually fades not because the object has fallen, but because it is moving into increasingly thinner air. The grazing encounter still leaves a mark. The rock loses some mass, some speed, and may change direction. The atmosphere removes energy even though it cannot hold the object. After moving away from Earth, it no longer follows exactly the same orbit it had before the encounter. The change may be small, but across long spans of time, even a slight difference in speed or direction can place the object on a new path around the Sunday. It may continue drifting through space, encounter another planet, or one day return near Earth. In some cases, a grazing trajectory can make it seem as though the object has bounced off the atmosphere. But there is no elastic surface pushing it back. It is simply following a path shallow enough that drag cannot remove all of its speed before its altitude begins increasing again. The actual trajectory is determined by the combination of inertia, Earth's gravity, and atmospheric drag. Gravity pulls the object downward, while its horizontal motion carries it forward. If the path is shallow enough and the speed remains high enough, the object can pass through the thickest part of the atmosphere and emerge again. A very small change in angle can lead to a completely different outcome. Slightly lower, the object may penetrate deeply, lose speed, and fall. Slightly higher, it may produce only a faint glow before continuing its journey. The difference between those two fates may lie in only a tiny variation in the original trajectory. Even so, entry angle should not be treated as the only deciding factor. A porous body may be destroyed while crossing only the upper atmosphere. A denser mass may penetrate deeply along a steep path. Large bodies preserve their motion more effectively, while small particles are strongly affected by drag. Greater speed increases heating and pressure, while structural strength determines how much stress the object can endure. Entry angle is therefore like the length of the path the atmosphere has available to do its work. A steep trajectory shortens that path but carries the object rapidly into denser air. A shallow trajectory extends the encounter, giving the atmosphere more time to erode, fragment, and remove speed from the object. The rock we have been following does not graze the atmosphere and return to space. Its entry angle is deep enough to keep the remaining fragments within the atmosphere. Most have already lost their speed, while the smaller particles gradually become part of the air. Its encounter is one of countless events in which the atmosphere receives material from space without leaving any clear trace on the ground. And most of the luminous streaks people see do not come from rare, massive rocks. They are produced by tiny particles within long streams of dust orbiting the sunday. At certain times each year, Earth passes through these streams of material, allowing dozens or even hundreds of streaks to appear one after another across the sky. Small particles of material do not always travel entirely on their own. Many are part of long streams of dust spread along the orbits of comets or certain asteroids. These particles may be scattered across millions of kilometers of space, far too thinly to form a cloud that can easily be seen, yet still concentrated enough for Earth to encounter large numbers of them as it passes through. A comet carries a mixture of ice, dust, and small pieces of rock. When its orbit brings it closer to the sun, its surface begins to warm. Some of the ice changes directly into gas, releasing particles that had once been trapped inside. Escaping gas creates the bright head and familiar tail, while dust is gradually deposited along the comet's path. Those particles do not remain motionless behind it. They continue orbiting the sun along paths similar to that of the body that released them. Each time the comet returns, more material is added to the stream. After many orbits, a broad band containing countless small particles forms along the path, like an immensely long road marked with cosmic dust. Earth is also moving around the sunday. If our planet's orbit crosses one of these dust streams, the encounter may repeat at nearly the same time each year. Earth enters a region containing a greater concentration of particles, and over several nights, the number of luminous streaks appearing in the sky increases noticeably. This is what we call a meteor shower. The name may create the impression of thousands of stars falling toward Earth, but the reality is far gentler. Most of the particles producing the display range in size from grains of sand to peas. Some are even smaller. They are extremely light, but because they travel at tremendous speed, they still carry enough energy to make the atmosphere glow as they enter. Each particle arrives at a different place in time. Some appear in the eastern sky, some almost directly overhead, and others only skim the horizon. Yet if their glowing paths are traced backward, they seem to converge on the same region of the sky. That region is known as the apparent radiant, or simply the radiant. It is not where the particles were actually created, nor is it a doorway through which they enter. It is only an effect of perspective, much like parallel railroad tracks appearing to meet far in the distance even though the space between them never changes. Before reaching Earth, the particles within the dust stream are moving along nearly parallel paths. But from the perspective of an observer standing on the surface, they appear to emerge from the same direction. The radiant's position in the sky is commonly used to name the meteor shower, usually after the constellation located nearby. The Perseids appear to radiate from the region of the constellation Perseus. The Leonids are associated with Leo, while the Orionids appear near Orion. These names help people identify the displays, but the particles do not actually come from the stars within those constellations. Those stars are unimaginably farther away, while the dust stream is passing through the region near Earth. Not every meteor shower comes directly from an active comet. The Geminids are an unusual example, associated with the object Phaethon, a body whose characteristics often place it closer to the asteroid category. Material along its orbit still produces one of the most reliable and prominent meteor showers each year. This shows that streams of particles within the solar system can form in several ways. Comets release dust as their ice warms. Asteroids may leave material behind after collisions, fractures, or processes that gradually remove small particles from their surfaces. Whatever their origin, once Earth encounters those particles, the atmosphere processes them according to the same familiar principles. A particle enters the thin upper atmosphere, and the number of collisions increases as it descends. The air ahead is compressed. A region of hot gas forms, atoms emit light, and the particle's surface is rapidly stripped away. Because the object is so small, the entire process may end within a fraction of a second. A streak of light appears, crosses a section of the sky, and vanishes. The particle may have been completely consumed before the observer even has time to turn and follow it. What remains becomes metallic vapor, atoms, and microscopic grains of dust mixed into the atmosphere. During a meteor shower, dozens or even more such streaks may appear in a single night, but each one is usually separated by an interval of quiet darkness. The sky is not filled with large rocks all falling at once. Earth is simply passing through a region where the concentration of small particles is higher than usual, and the atmosphere receives them one by one. A bright meteor shower is therefore not a sign of a dangerous bombardment. It is one of the clearest visible demonstrations that the atmospheric shield is continuing its ordinary work. Particles carrying tremendous speed enter, glow high above, and lose most of their mass before they can approach the ground. This is also why it is nearly impossible to go outside the following morning and easily collect meteorites from a meteor shower. Most of the particles are too small and porous to survive. They are eroded or vaporized at high altitude, leaving no fragments large enough to recognize on Earth's surface. Even if a tiny remnant survives, it may be only a micrometeorite, so small that it is difficult to distinguish from ordinary dust. After falling through many atmospheric layers, it may land in an ocean, forest, desert, on a rooftop, or anywhere else across Earth's vast surface. The chance of finding it and correctly identifying its origin is therefore extremely small. Meteorites are more often found after fireballs produced by larger individual objects than after ordinary meteor showers. In those cases, cameras or eyewitnesses may help determine the flight path, the altitude of fragmentation, and the region where surviving pieces may have fallen. With the small dust particles responsible for meteor showers, there is usually no remaining material large enough to produce a clearly defined strewn field. The difference between a meteor shower and a single large object lies not only in the number of luminous trails, but also in the amount of energy concentrated within each object. A dust stream may contain countless particles, but each one carries only a tiny amount of material. They enter separately and release their energy high in the atmosphere, so the overall effect at the surface is almost non-existent. A single larger rock carries far more mass within one object. It may preserve its speed over a longer path, penetrate more deeply, and transfer energy into the atmosphere within a more concentrated region. Even though it produces only one luminous trail, it may sometimes be more significant than hundreds of small meteors appearing during the same night. Meteor showers also show that the atmosphere does not need to eliminate every piece of material in exactly the same way. Some particles vaporize completely. Some break into even smaller dust. Some are so light that they slow early and continue drifting downward gently. but nearly all of them lose their dangerous cosmic speed before reaching the lower atmosphere. During a meteor shower, people on the ground can lie still and watch one streak after another pass overhead. Between appearances are long stretches of darkness, giving the sky enough time to return to its original calm. No sound reaches the surface because the events usually occur too high and involve objects too small to produce noise that can be heard below. Each luminous trail lasts only a moment, but the dust stream that created it may remain around the sun for centuries. Earth passes through, draws a very small portion of that material into the atmosphere, and then continues along its orbit. The following year, the planet returns to nearly the same place and encounters other particles still traveling along the old path. Through these repeated encounters, the atmosphere quietly absorbs a considerable amount of material. Each particle is too small to attract attention on its own, but when many appear during a meteor shower, they allow people to witness a process that continues constantly and usually goes unnoticed. The thin shield surrounding Earth does not need to open or close. It is simply always there, receiving incoming dust, removing its speed, and transforming part of its motion into brief lines of light. Beneath that layer of gas, the oceans and continents experience almost no change at all. On most nights, encounters with cosmic material end this gently. A particle glows, disappears, and the sky becomes dark again. But sometimes, what enters the atmosphere is no longer a tiny grain from a cometary dust stream. A much larger object arrives, carrying enough energy to create a point of light far brighter than any ordinary meteor. Then the luminous trail does more than simply cross the sky. It may flare so intensely that for a few seconds, the landscape below appears as though it were illuminated by daylight. Among the countless small particles that create meteor showers, a larger object occasionally appears along an orbit of its own. Instead of leaving only a thin streak of light before disappearing, it may cause an entire region of the sky to flare for several seconds, bright enough to reveal the ground, rooftops, and rows of trees below in a light that does not belong to daytime. An unusually bright meteor like this is often called a fireball. The name does not mean that a sphere of material is burning like an ordinary flame. It mainly describes the brightness seen by an observer. When a meteor shines far more brightly than most stars and planets in the sky, the event is classified as a fireball. The object producing a fireball is usually larger than the dust particles in a meteor shower, but size is not the only factor. A smaller rock entering at extremely high speed may still glow intensely. A larger object that is porous, weak, and breaks apart early may release its energy at high altitude, creating a broad flash before quickly fading. Composition, density, entry angle, and fragmentation altitude all help determine what people see. As the object races through the atmosphere, the air ahead continues to be compressed and heated. The surface undergoes ablation, material breaks away, and atoms within both the atmosphere and the rock itself emit light. If the object preserves a high speed while penetrating deeper, the amount of energy transferred into the atmosphere each second can rise dramatically. Brightness, therefore, does not tell us only how much material is present. It also reflects the rate at which kinetic energy is being converted. An object that releases most of its energy within a very short time may shine far more brightly than one that loses energy gradually along a longer path. A fireball may sometimes appear only as a large moving point of light. In other cases, it flares in several pulses, producing powerful bursts as different parts of its internal structure break apart in succession. Every fragmentation event exposes additional surface area, causing the material to heat and ablate more rapidly. When the fragmentation is especially violent, the event is often called a bolide. This term is not always used in exactly the same way in every source, but it generally refers to a very bright fireball involving violent breakup or a particularly prominent release of energy within the atmosphere. Even more luminous events are sometimes called superbolides. These are rare events with extremely great apparent brightness and are generally associated with objects carrying far more kinetic energy than ordinary meteors. Even so, the boundaries between a fireball, bolide, and superbolide are mainly useful for describing the observed scale of an event rather than defining three completely separate kinds of objects. The same object may begin as a bright meteor, develop into a fireball, and then undergo a powerful fragmentation event described as a bolide. These names help distinguish the scale and appearance of the phenomenon, while the underlying physics remains the same: transfer of energy between the object and the atmosphere. If a large rock breaks apart violently while it is still traveling at high speed, its remaining energy may be transferred into the air over a very short period. The object does not necessarily reach the ground. Instead, it is destroyed within the atmosphere, producing what is commonly called an airburst. The word explosion may suggest that the object contains explosives or chemical fuel, but an airburst caused by a celestial body requires neither. The energy is already present in the object's motion. When the rock is rapidly slowed and fragmented, its kinetic energy is transferred into the air, causing a region of gas to heat, compress, and then expand forcefully. That expansion creates pressure waves that spread outward from the flight path. Near the object, the disturbance may form a powerful shock wave. As it travels farther, the wave gradually weakens, but it can still affect the ground if the energy is great enough and the release does not occur too high above the surface. In this case, the atmosphere has prevented the intact object from striking the ground. It may avoid a direct impact and leave no obvious crater, but the energy does not disappear with the rock. The shield merely transforms the danger from a descending mass into light, heat, fragments, and pressure waves traveling through the air. The altitude at which this process occurs greatly influences the effects below. If the object breaks apart high in the atmosphere, the pressure waves have more distance over which to spread and weaken before reaching the ground. The energy is distributed across a larger region, usually reducing its effect at any one location. If the object remains intact longer and breaks apart at lower altitude, the shock wave has less distance in which to weaken. The energy may be concentrated over a smaller region, causing stronger pressure at the surface. Two objects with similar initial energies can therefore produce very different outcomes if they fragment at different altitudes. Entry angle also continues to play a role. A shallow trajectory may spread energy along an extended path. A steep trajectory can carry the object quickly into denser air and concentrate its deceleration within a narrower region. Composition and structural strength determine how much aerodynamic stress the object can withstand before breaking apart. When a fireball appears, its light almost always reaches observers before its sound. Light travels from the altitude of the event to the surface almost instantaneously from a human perspective, while sound moves through air far more slowly. A person may therefore see the sky flash, watch the luminous trail disappear, and then wait some time before hearing an explosion or a series of deep, prolonged rumbles. If the event occurs tens of kilometers away, the delay may last several minutes. The sound does not always arrive as a single explosion. An object following a long path through the atmosphere can create multiple pressure waves along its route. People in different locations may hear them at different times, depending on their distance and the shape of the flight path. Some of the acoustic energy also travels at frequencies below the range of human hearing. These vibrations are known as infrasound. They can cross enormous distances through the atmosphere and be detected by specialized instruments even when the event itself was not directly observed. Infrasound data helps scientists estimate the object's location, energy, and pattern of fragmentation. Cameras, satellites, and light sensors provide additional information about its brightness and trajectory. By combining these measurements, researchers can reconstruct a fairly detailed journey from a flash that lasted only a few seconds. Most fireballs still end at high altitude and cause no damage on the ground. They may glow intensely, leave a long-lasting ionized trail, and then disappear. Impressive brightness does not automatically mean that an event is dangerous. An object may look extraordinarily bright precisely because the atmosphere is removing its energy so effectively. In some cases, surviving fragments continue falling after the luminous phase ends. They enter dark flight, are shifted by winds, and may produce a strewn field on the ground. But most of the original energy has already been transferred into the atmosphere, so those smaller fragments are no longer descending at cosmic speed. At a larger scale, an airburst reveals both the power and the limits of the atmospheric shield. The atmosphere can destroy an object before it creates a crater. But if the kinetic energy is great enough, the resulting shock wave can still shake windows, damage buildings, and affect people below. One of the clearest recorded examples began on a winter morning in 2013. The sky above the Chelyabinsk region of Russia was already bright with daylight when an object that had not been detected beforehand entered the atmosphere. Within seconds, it created a trail that appeared brighter than the sun from some locations. The light arrived first, while the shock wave was still traveling through the air. That encounter would demonstrate how the atmospheric shield can save a city from a direct impact, yet cannot always prevent every consequence from reaching the ground. The morning of the 15th of February 2013 began like an ordinary winter day in the Chelyabinsk region of Russia. Snow covered rooftops and roads, traffic was beginning to move, and daylight had just spread across the horizon. No one on the ground knew that a small object was approaching Earth from a direction close to the sun, where the glare made it extremely difficult for ground-based telescopes to detect in advance. The object was estimated to be about 17 to 20 meters across, roughly comparable to the width of a house. In space, it was not especially large compared with the countless asteroids orbiting the Sunday, but as it entered the atmosphere at around 18 to 19 kilometers per second, the rock carried an enormous amount of kinetic energy. In only 1 second, it could cross a distance that would take a car many minutes to travel. That motion had continued through space with almost no resistance until the object began encountering the outermost layers of gas surrounding Earth. Its trajectory was relatively shallow. Instead of plunging almost directly toward the surface, the object traveled diagonally through the atmosphere, extending its journey across a broad region. This angle of approach forced it to pass through a long path of air, while also creating a luminous trail visible from many different locations. During the first few seconds, the object retained nearly all of its speed. The air ahead could not move aside quickly enough and was compressed into a curved shock wave surrounding the leading edge. The compressed gas heated up, molecules broke apart, and some atoms became ionized. The rock's surface began losing material as the surrounding gas and mineral vapor glowed with increasing intensity. From the ground, a point of light appeared and quickly stretched into a long trail. Its brightness increased within only a few seconds, becoming so intense that from some locations, its apparent brightness exceeded that of the Sunday. Brief shadows appeared across the snow, the winter sky flared with light, and many dashboard cameras in passing vehicles recorded the entire flight. Those recordings later became an exceptionally valuable source of data. They allowed scientists to compare timing, location, viewing angles, and changes in brightness from many different points. Instead of relying only on eyewitness accounts, the event had been preserved by numerous cameras operating throughout the city and along nearby roads. The luminous trail did not remain steady. As the object penetrated deeper, atmospheric density increased and aerodynamic pressure acted more strongly on its surface. Fractures inside began to widen. The rock may have carried damage produced by earlier collisions in space, but only after entering the atmosphere were those weak points exposed to a load increasing so rapidly that the structure could no longer hold together. The object began to fragment. One mass separated into several pieces, and the larger pieces continued breaking into smaller fragments. Each time this happened, more new surfaces were exposed to the hot airflow, increasing the rate of ablation and causing the light to flare. Most of the energy was released at altitudes above 20 kilometers. The object did not remain intact and continue directly toward the city. The atmosphere had done what it routinely does to smaller objects: heat it, erode it, break it apart, and remove its speed. But the Chelyabinsk event was far larger than an ordinary meteor. When a house-sized rock is slowed and fragmented over a short period, its kinetic energy does not disappear. It is transferred into the surrounding air, heating a region of gas and causing it to expand rapidly. This was an airburst, but not an explosion caused by explosives or a chemical reaction. The energy was already present in the object's motion. The atmosphere was simply where that energy was released in the form of light, heat, shock waves, and violent movement of the air. The total energy of the event was estimated to be equivalent to hundreds of kilotons of TNT. Numbers like these may sound enormous, but the important point lies in how the energy was distributed. Most of it was released high in the atmosphere and spread along the flight path rather than concentrated at a single point on the ground. If the rock had remained intact and struck the surface directly at its original speed, the consequences would have been very different. A large portion of its kinetic energy could have been transferred into the ground within an extremely short time, creating a crater and devastating the area surrounding the impact point. That did not happen at Chelyabinsk. The atmosphere destroyed the object before it could reach the ground as a single intact mass. Earth's natural shield transformed a direct impact into a high-altitude release of energy. But that transformation did not make every danger disappear. Light from the event reached the ground almost immediately, while the pressure wave still needed time to travel through tens of kilometers of air. People therefore saw the luminous trail before they heard any sound. Some moved closer to windows to watch. Others pointed cameras toward the sky. During those first moments, the glowing trail had already vanished, creating the impression that the event might be over. But the shock wave was still traveling downward. After a delay, the blast arrived. Windows shook and shattered across a wide area. Buildings suffered varying degrees of damage. Roofs and walls were affected, and countless pieces of glass were thrown into interior spaces. About 1,600 people were reported injured, most not because meteorite fragments struck them, but because of broken glass and other indirect effects of the shock wave. This is an important detail of the event. The object had been destroyed high above the ground, yet the energy transferred into the atmosphere was still strong enough to cause damage at the surface. Chelyabinsk therefore shows that the atmospheric shield does not simply stop an object or fail to stop it. It changes the form of the danger. Instead of a large rock striking the city, the energy arrived as a pressure wave spread across a broad region. The altitude of fragmentation played a decisive role. Because most of the energy was released more than 20 kilometers above the ground, the shock wave had time to spread and weaken. If the same amount of energy had been released much lower, the pressure at the surface could have been stronger. If the object had broken apart higher, the effects below might have been reduced even further. The shallow trajectory also helped distribute the energy along an extended path rather than concentrating it at a single point. This made the event visible across a very wide area, but it also allowed the atmosphere to stretch out the process of fragmentation and deceleration. Each section of the path received part of the energy, instead of all of it being released directly at the surface. Not all of the asteroid's material became vapor. Some fragments were large enough to survive the luminous phase, lose nearly all of their cosmic speed, and enter dark flight. They continued falling under gravity and were carried away from the original path by winds in the upper atmosphere. Many small fragments were found throughout the region after the event. Some material fell near Lake Chelyabinsk, where a large hole appeared in the ice. Later, a substantial meteorite fragment was recovered from the bottom of the lake, along with many smaller pieces collected from the surrounding snow and ground. The surviving fragments did not preserve the intact shape of the original object. Their surfaces carried thin fusion crusts, their edges had been altered, and their structures revealed a history of fragmentation within the atmosphere. Inside, however, ancient material remained well preserved enough for scientists to study. Their mineral and isotopic composition helped identify the Chelyabinsk object as belonging to a fairly common group of stony meteorites. Internal traces also recorded collisions that had occurred long before the rock approached Earth. The object's history did not begin on that morning in 2013. It had existed within the solar system for an immense span of time, once forming part of a larger body before being released into space. The meteorite samples were only one part of the evidence. Dashboard cameras allowed researchers to reconstruct the atmospheric trajectory. Satellites recorded the powerful flash from above. Infrasound stations at great distances detected pressure disturbances below the range of human hearing. Infrasound can travel across enormous distances through the atmosphere. By comparing when the waves reached different stations, researchers estimated the location and energy of the airburst. These measurements added further detail to the camera footage and the fragments recovered from the ground. When the different sources of information were combined, the object's journey gradually became clear. It approached from a direction that was difficult to observe, entered at around 18 to 19 kilometers per second, followed a relatively shallow trajectory, produced an intense light, fragmented high above the ground, and released most of its energy into the atmosphere. Only a few seconds of flight produced enough data for scientists to study for years. Chelyabinsk became one of the clearest examples of how the atmosphere responds to a medium-sized object, too large to be consumed gently like a grain of dust, but not large enough to preserve most of its energy all the way to the surface. The event also showed that an object going undetected beforehand does not necessarily mean observation systems overlooked an obvious, bright target. The Chelyabinsk object approached from a region of the sky near the sun, where daylight glare made it extremely difficult for ground-based observatories to see a small, dark rock moving toward Earth. Its size also placed it within a range that is difficult to detect from far away. An object around 20 meters across is far smaller than the large asteroids commonly tracked over long periods, yet it can still carry enough energy to produce a significant airburst during atmospheric entry. Chelyabinsk is not evidence that major disasters are constantly waiting above cities. Events of this scale are far rarer than the small meteors appearing every night. Most material entering the atmosphere is still consumed without producing any effect that can be felt at the surface. But the event reminds us that the shield works in several different ways, and each has limits. For small particles, the atmosphere can remove nearly all of their material and speed. For an object the size of the Chelyabinsk body, it can break the rock apart and prevent a direct impact. But it must still absorb an enormous amount of energy. The atmosphere saved the region from an intact rock striking at cosmic velocity. No large crater appeared in the middle of the city. Most of the object became vapor, dust, and small fragments. Yet the shield could not keep the shockwave high above the ground. Energy traveling through the air still reached windows, rooftops, and the people standing below. This is why Chelyabinsk can be seen as a successful but incomplete act of protection. The shield greatly reduced the scale of the disaster that might have occurred, but it could not make such a large amount of kinetic energy completely harmless. As the size of an incoming object increases, that balance begins to change. Mass grows more quickly than surface area, allowing the body to preserve its speed more effectively. Its core is protected at greater depth, while the atmosphere becomes less capable of removing all its energy before it descends into the lower layers. Chelyabinsk showed that the atmosphere can destroy an object roughly the size of a house, but if the rock is much larger, denser, or stronger, increasing amounts of kinetic energy may survive the journey. And at that point, the thin shield around Earth begins to approach its own limits. Chelyabinsk showed that a thin layer of gas can break apart an object nearly the size of a house before it reaches the ground. But that protection does not continue increasing indefinitely as the object grows larger. A bigger body carries more mass, preserves its velocity more effectively, and contains more material deep inside, where heat and drag have difficulty reaching during the few brief seconds of atmospheric entry. The atmosphere still heats the surface, removes material, and creates enough pressure to widen fractures. However, the relationship between the area exposed to the air and the object's mass gradually changes. A large body contains more material behind every square meter of surface than a small fragment does. The same layer of atmosphere may therefore erase a pebble completely, while removing only the outer layers of a much larger body. There is no single size that marks the exact point where this protection ends. A porous object may break apart at high altitude, while a smaller but metal-rich body penetrates more deeply. Entry angle, velocity, strength, and internal structure continue to alter the outcome. Even so, once the object becomes large enough, it grows increasingly difficult for the atmosphere to disperse all of its kinetic energy before powerful effects reach the ground. A clear example occurred more than a century before Chelyabinsk, over a sparsely populated forest region in Siberia. On the morning of the 30th of June 1908, an object from space entered the atmosphere above an area near the Tunguska River. No dashboard cameras, observing satellites, or modern sensor networks recorded its flight. What remained were eyewitness accounts, traces on the ground, and a vast region of forest transformed within only a few seconds. People far from the site described a brilliant light in the sky, followed by explosions and vibrations passing through the ground. When expeditions reached the region years later, they found millions of trees knocked down, with their trunks pointing outward around a broad central area. Yet there was no clearly defined impact crater large enough to match the scale of the destruction. This suggests that the Tunguska object most likely did not strike the ground as an intact body. It penetrated deeply into the atmosphere, encountered rapidly increasing pressure, then fragmented and released most of its energy in the air. The basic mechanism was similar to Chelyabinsk, but on a much larger scale. The atmosphere prevented the object from producing a direct impact, but the high-altitude explosion still caused a region of heated gas to expand violently. The shock wave traveled downward into the forest, breaking and flattening trees across a vast area. Near the center, some trunks remained standing but had been stripped of branches and bark, suggesting that the pressure wave traveled almost directly downward before spreading outward. Tunguska reminds us that an object does not need to reach the ground to cause severe effects. If it is large enough, it can transfer an enormous amount of kinetic energy into the atmosphere at low altitude. The shield may still destroy the object, but the air then becomes the medium carrying the shock wave toward the surface. This was not a complete failure of the atmosphere. If the object had remained intact and struck the ground while preserving most of its original speed, a large crater and more concentrated effects might have formed. But it cannot be described as complete protection either. The atmosphere changed the form of the event without erasing the energy carried by the incoming body. Tunguska occurred above a sparsely populated region, so the consequences for people were limited. If a similar event took place over a major city, shock waves, heat, and shattered glass could produce very different damage. Even so, events of this scale are far rarer than the small meteors that appear every night. Elsewhere on Earth, the atmosphere was unable to prevent a denser object from reaching the surface. In Arizona, a broad and clearly defined impact crater lies within the dry landscape, commonly known as Meteor Crater. It formed about 50,000 years ago when an iron-rich object struck the ground at tremendous speed. The body did not necessarily preserve its entire original shape throughout the descent. Its surface still experienced ablation, and some fragmentation may have occurred, but its iron-rich composition gave it greater density and strength than many porous rocks. It retained enough mass and velocity to continue downward, passing beyond the stage where the atmosphere could slow it to an ordinary falling speed. When it reached the ground, the object was still moving at hypervelocity. This was no longer a small meteorite descending after dark flight. Energy was transferred into the surface so rapidly that the ground had no time to move gently aside. Extreme pressure crushed, heated, and threw material outward, creating a crater far wider than the object itself. In an impact like this, The incoming body does not simply dig a hole by pressing the ground downward. It releases energy within an extremely short time, producing shock waves that travel through the material. Rock and soil are lifted, thrown outward, and deposited around the crater rim. Most of the impactor is also destroyed, melted, or scattered into small fragments. Meteor crater shows how composition can change the depth to which an object penetrates the atmosphere. An iron-rich body is usually denser than an ordinary stony meteorite and may preserve its kinetic energy more effectively. But this does not mean every iron object creates a crater or that every stony object explodes in the atmosphere. Size, angle, speed, and internal structure must still be considered together. Between Chelyabinsk, Tunguska, and Meteor Crater lies a continuous range of outcomes rather than a set of separate categories. An object may be consumed completely, break into small meteorites, produce an airburst, or reach the ground at a speed high enough to form a crater. Changing only a few characteristics can cause objects of the same original size to meet very different fates. As the scale continues to increase, the atmosphere's relative role becomes smaller. A large celestial body can carry an enormous mass and kinetic energy far beyond what the layer of gas can disperse. The atmosphere still acts on its outer surface, creating shock waves and removing some material, but the energy lost may represent only a very small fraction of the object's original total. The event that created the Chicxulub crater is an example at this scale. About 66 million years ago, a celestial body several kilometers across struck the region that now lies near the Yucatan Peninsula. For an object that large, the atmosphere could not slow it significantly before it reached the surface. The layer of gas around Earth was still compressed and heated violently. Shock waves spread outward, while the object's surface endured extreme processes, but most of its mass and kinetic energy continued downward. During the final few seconds, the remaining distance through the atmosphere was too short and the time too limited for the shield to alter the outcome in any fundamental way. The impact created an enormous crater structure, released energy on a global scale, and sent dust, water vapor, and intensely heated material into the atmosphere. The changes that followed lasted far longer than the impact itself. This was the kind of event the atmosphere could never prevent, because the layer of gas contained far too little material compared with the body descending through it. Viewed from a distance, the difference between these scales becomes clearer. A grain of sand encounters an enormous amount of air relative to its own mass, so it is quickly slowed and consumed. A large rock encounters the same atmosphere, but contains far too much mass for the air to process completely. The shield still has an effect, but it is no longer powerful enough to determine the object's entire fate. The role of the atmosphere becomes even clearer when Earth is compared with the Moon. The Moon has almost no atmosphere thick enough to slow or erode incoming objects. A small rock can travel from space to the lunar surface while losing almost none of its velocity to drag. As a result, the Moon's surface is covered with countless impact craters of many different sizes. These marks overlap and can survive for immense spans of time because there is no rain, flowing water, or powerful wind to erase them. Every crater records an object that traveled directly to the ground without encountering a significant atmospheric shield. Earth has also received countless similar objects, but many small particles and rocks were destroyed by the atmosphere before reaching the surface. The craters that did form were then altered by erosion, water, ice, vegetation, and geological activity. Plate tectonics can carry old sections of crust deep below the surface, while sediment buries structures that were once clearly visible. Earth's smaller number of easily recognized craters therefore does not mean that our planet rarely encounters material from space. Some of the evidence has been erased by the active surface. Other marks never formed at all because the atmosphere intercepted the objects beforehand. This shield is most effective during the encounters that happen most often: dust, grains of sand, pebbles, and small rocks. It slows, heats, erodes, and fragments them high above the surface. With medium-sized objects, it may still prevent a direct impact, although it can sometimes transform the danger into an airburst. As an object becomes larger or denser, a significant portion may continue toward the ground, and for a celestial body several kilometers across, the atmosphere becomes only the first layer it passes through, not a barrier capable of fundamentally changing the outcome. Yet no simple boundary exists between these extremes. We cannot say that every object below a certain diameter will certainly disappear while every larger one will reach the ground. A porous body may break apart early, an iron-rich object may penetrate deeply. A shallow trajectory extends the flight, while a steep one carries energy lower into the atmosphere. High velocity greatly increases kinetic energy, and internal fractures determine when the structure collapses. The atmosphere is therefore not a shield that is simply open or closed. It is an environment that continuously transforms the fate of an incoming object. Sometimes it allows a dust particle to slow and settle almost intact. Sometimes it turns a stone into a streak of light. Sometimes it tears a large body into countless fragments. And sometimes, even after removing some of its material, it must allow the remainder to continue downward. The rock we have been following experienced the gentler side of that limit. Most of its material was consumed high above, and the surviving fragments no longer retain their cosmic velocity. They are falling through the darkness, drifting under the influence of upper-level winds, and gradually slowing before reaching the ground. Between dust particles that are completely destroyed and asteroids large enough to overcome the shield lies an entire range of possible outcomes. Some fragments still reach the surface, but by then they are very different from the objects that first entered from space. Their speed has been removed, their outer layers have been transformed, and their final path is no longer determined only by the original orbit, but also by the wind and the last layers of atmosphere through which they fall. The surviving fragments have now passed through the most violent part of the encounter. The shock waves around them have weakened. The heated gas is no longer intense enough to sustain a luminous trail, and speeds that once reached tens of kilometers per second have fallen dramatically. From the ground, the streak of light appears to end in midair. But for some pieces of material, the journey is not yet over. They have entered the stage known as dark flight. The name does not mean the object has vanished. It only means the rock is no longer glowing brightly enough for the human eye or an ordinary camera to continue seeing it. From a cosmic object racing through the atmosphere, it has become a stone falling through the air under the influence of gravity, drag, and wind. The change is enormous. During the luminous phase, the object traveled many kilometers in a single second. After losing its cosmic speed, it may need several more minutes to complete the remaining descent. This longer period allows atmospheric currents to shape its path in ways they could not while it was still moving at extreme velocity. At high altitude, winds may blow in directions very different from those near the ground. A meteorite fragment passing through several atmospheric layers can be pushed in different directions one after another. In one region, it may drift eastward. Lower down, another current may carry it north or south. Its descent is therefore rarely a simple straight line connecting the point where the luminous trail disappeared with the ground below. Smaller fragments are affected most strongly. They contain little mass but have a relatively large area exposed to the air, making it easier for drag and wind to alter their motion. A small piece may be carried far from the original flight path, while a larger mass generally retains more momentum and continues farther along its earlier direction. Gravity still pulls every fragment downward, but the speed does not increase forever. As a rock falls faster, aerodynamic drag also grows stronger. Eventually, the downward pull of gravity and the upward force of drag approach a near balance. The fragment reaches terminal velocity, continuing to fall without accelerating significantly. Terminal velocity depends on mass, shape, and surface area. A dense, heavy, compact fragment can fall faster than a lightweight, flat, or irregularly shaped one. If the object tumbles chaotically, the area facing the airflow changes continuously, causing both its speed and direction to fluctuate. Although some fragments still strike the ground with considerable force, this speed is far lower than the velocity they carried when they first entered the atmosphere. An object that once possessed enough energy to create a glowing region of hot gas may now be falling at speeds similar to an ordinary object dropped from a great height. It can still dent a roof, penetrate a thin layer of material, or create a small depression in the ground, but it does not necessarily produce an explosion or a large crater. This is the important difference between a small meteorite falling after dark flight and a celestial body that retains hypervelocity when it strikes. In the second case, energy is released almost instantly and can shatter rock and soil across a large region. In the first, most of the dangerous kinetic energy has already been transferred into the atmosphere. When the original object fragments, the surviving pieces usually do not fall at the same point. They form an elongated region across the ground, known as a meteorite-strewn field. The shape and size of this area depend on the trajectory, fragmentation altitude, fragment sizes, and atmospheric winds. Larger fragments usually preserve their direction more effectively and tend to travel farther along the original path. Smaller pieces are slowed more strongly by drag and are more easily pushed sideways by wind or left farther behind. When researchers map a strewn field, they can sometimes identify a rough size-related arrangement among the recovered fragments. But nature rarely produces a perfectly orderly pattern. The object may fragment several times at different altitudes. Some pieces may continue breaking apart during dark flight. Terrain, forests, rivers, lakes, and snow cover can also make the search difficult. One fragment may land in an open, visible place, while another sinks into water or becomes buried in soft ground. If a fragment is found soon after it falls, its surface may carry a dark coating known as a fusion crust. This layer forms during the luminous phase, when the outermost material is intensely heated and briefly melts. After the object slows down, the molten surface cools and solidifies into a thin crust surrounding what remains. A fusion crust is usually only a tiny fraction of the meteorite's overall thickness. It does not mean the entire rock once melted. Directly beneath that crust, the internal structure may remain largely unchanged. Ancient minerals, grains of metal, and traces of processes that occurred long ago can still be preserved. If a meteorite remains exposed to the environment for a long time, its crust may weather, crack, or change color. Iron inside reacts with water and oxygen, creating patches of brown rust. In a desert, a specimen may survive for a long time while remaining relatively easy to recognize. In a humid climate, the surface may change more quickly and gradually begin to resemble the ordinary rocks around it. Some meteorites have shallow depressions across their surfaces, often compared to fingerprints pressed into soft clay. These shapes may form when hot airflow erodes the surface unevenly during the luminous stage. They are sometimes called aerodynamic depressions. Not every meteorite has these features, and not every stone with a pitted surface came from space. Water, wind, and weathering on Earth can create many similar shapes. A single characteristic is therefore not enough to determine an object's origin. A newly fallen meteorite is often portrayed as a red-hot, smoking rock, hot enough to burn the ground beneath it. In many cases, however, this image does not accurately reflect what really happens. The period of intense heating lasts only a few seconds and mainly affects an extremely thin outer layer. The core may remain much colder because heat has too little time to travel deeply into the material. After the object slows, it may continue falling through cold atmospheric layers for several minutes. During that time, the exterior continues exchanging heat with the surrounding air. A meteorite that has just reached the ground may still be warm, but it may also be close to the temperature of the surrounding air and not necessarily hot enough to cause a burn when touched. This does not mean every meteorite is safe to pick up immediately. A newly fallen object may have sharp edges, and a sufficiently large fragment can still carry considerable momentum. More importantly, When a scientifically valuable specimen is found, touching it with bare hands can transfer oils, moisture, and material from Earth onto its surface, contaminating evidence that researchers may need to analyze. A dark stone lying on the ground does not automatically qualify as a meteorite. Earth contains countless iron-rich rocks, volcanic stones, industrial slag, and human-made materials that can closely resemble specimens from space. Some attract magnets, have black surfaces, or feel unusually heavy, yet are entirely terrestrial in origin. Verification usually requires several lines of evidence considered together. Researchers examine the surface crust, internal structure, density, minerals, metallic content, and chemical composition. Some stony meteorites contain small rounded grains formed during the early solar system. Iron meteorites may reveal distinctive metallic structures only after a sample has been properly cut, polished, and treated. Laboratory analysis is needed for a reliable conclusion. Isotopic ratios, mineral composition, and microscopic structure help distinguish extraterrestrial material from ordinary Earth rocks. When the specimen was observed falling and its trajectory was recorded by cameras, connecting it to a particular event becomes even more certain. Falls tracked from beginning to end are especially valuable. All sky cameras can record the luminous trail, allowing researchers to calculate its direction and speed. Wind data helps predict the dark flight path. Search teams can then survey the strewn field and collect fragments before rain, soil, and human activity alter them. Each recovered piece can provide another part of the original object's story. Larger fragments reveal deeper internal structures, while smaller pieces help show how the body broke apart. Their landing positions also allow researchers to test models of drag, wind, and terminal velocity. The rock we have been following has finally reached the last stage of its journey. After the light, heat, and repeated fragmentation, only a small fraction of its original mass continues downward. Winds carry it away from the earlier trajectory. It turns slowly through the air, and it gradually cools as its altitude decreases. The moment it reaches the ground produces no great explosion. The fragment falls into soft soil, bounces a short distance, and comes to rest. Its dark surface carries a thin crust that has already solidified. Inside is material that had never encountered Earth's water, air, or life until that moment. Most of the original object remained behind in the atmosphere as metallic vapor and dust. Other fragments landed farther away. Only a small part of a journey lasting millions of years ended within the stone now resting on the ground. Its value, however, does not lie in its size. Beneath the crust that passed through fire are minerals formed before the planets reached their present shapes. The atoms inside carry information about age, composition, and collisions that occurred in places no human being has ever visited. The surviving fragments are therefore more than the remains of a passage through the atmosphere. They are natural samples delivered to Earth from the distant past, carrying information from an era before the planets had fully formed. The rock resting quietly on the ground may be small enough to fit in the palm of a hand. Its outer surface has been transformed by the atmosphere, but the material deep inside still preserves a story that began before Earth had oceans, continents, or the familiar atmosphere we know today. Once it is carefully collected and taken into a laboratory, the rock is no longer merely the remnant of a streak of light. It becomes a sample that can help humanity look back to the era when the solar system was still forming. Scientists first examine the structure of the specimen. An extremely thin slice may be placed under a microscope so that light can pass through its minerals. The colors, crystal shapes, and arrangement of small grains reveal the conditions under which the material once formed. Some minerals experienced high temperatures, some regions were altered by water, and certain fractures show that the rock endured powerful impacts long before it encountered Earth. Its chemical composition adds other parts to the story. Instruments can determine how much iron, nickel, magnesium, silicon, and many other elements are present. Even a very small amount of material can reveal which group the meteorite belongs to, whether it once existed within a body that melted and separated into layers, or whether it still preserves a primitive structure from the earliest days of the solar system. One of the most important groups of meteorites is known as chondrites. The name is connected to the small rounded grains found inside many of these rocks, which formed when droplets of molten material cooled within the cloud of gas and dust surrounding the young sunday. Those grains later joined with dust, metal, and other mineral fragments to form some of the first small bodies in the solar system. Many chondrites have never completely melted since they formed. Because of this, they preserve an extremely ancient mixture of material, similar to the ingredients that helped create the planets. When scientists study them, they are not looking at a finished world, but at small pieces of the process that existed before rock, metal, and ice came together to build larger worlds. Some meteorites even contain grains of material older than the sun itself. These particles formed around stars that lived and died before the solar system was born, then became part of the cloud of gas and dust from which the sun and planets emerged. These microscopic grains are almost like samples from an earlier generation of stars, preserved within meteorites for billions of years. The age of the material can be determined through isotopes. Some elements exist in several forms with slightly different masses, and certain unstable isotopes transform into other isotopes at measurable rates. By comparing the original isotope with the products created over time, scientists can estimate when a mineral formed or when an event altered the system within it. These measurements show that many meteorites are nearly as old as the solar system itself, about 4.6 billion years. This number does more than reveal how long the rock has existed. It also helps establish when the first solid objects formed around the sun and when the planets began growing from smaller pieces of material. Isotopic traces can also reveal a history of heating. If a parent body was once warmed, struck, or altered by water, some isotopic systems inside it may have been reset or rearranged. By comparing different minerals, researchers can gradually reconstruct a sequence of events that occurred long before the rock broke free and began traveling on its own. Among these samples, carbon-rich meteorites hold a special place. They are often dark, relatively fragile, and filled with material that can be easily altered after contact with Earth's environment. Some contain minerals that once reacted with liquid water on their parent bodies, showing that small objects in the early solar system were not always completely cold and dry. The water in these meteorites is usually not trapped as droplets of liquid. Instead, it is chemically bound within the structure of minerals, becoming part of the solid material after reactions that occurred long ago. Finding hydrated minerals allows scientists to study how water was distributed among young celestial bodies and the possible routes by which it may have been delivered to planets. Carbon-rich meteorites also contain many organic compounds. In science, the word organic mainly refers to carbon-based compounds. It does not mean that they were produced by living organisms. Organic molecules can form naturally in space, on the surfaces of dust grains, within ice, or inside small celestial bodies, without the presence of life. Finding organic compounds in meteorites, therefore, does not prove that fully formed life was delivered to Earth. Nor does it mean that organisms once lived inside the rock. The importance of the discovery is that complex chemical ingredients were already present very early in the solar system, before life is known to have existed on our planet. Some meteorites contain amino acids and many other kinds of carbon-based molecules. These compounds help scientists investigate how prebiotic chemistry may have occurred beyond Earth. They show that ingredients needed for complex chemical processes did not form only on planetary surfaces, but could also arise in many different environments and then spread throughout the solar system. Sensitive samples like these, however, are extremely vulnerable to contamination. Contact with soil, water, air, or human hands can add organic compounds from Earth to the meteorite. This is why observed falls that are collected quickly are especially valuable. The less exposure a sample has to the outside environment, the more accurately its internal evidence can be interpreted. Not all cosmic material reaching Earth is found as a stone large enough to hold. Most of it is far smaller. Every day, micrometeorites and cosmic dust settle into oceans, snow and ice, deserts and land. They blend into the natural environment so completely that most people never notice their presence. In places with little contamination from human-generated dust, researchers can search for these tiny particles. Long-preserved ice, deep-sea sediments, and remote regions far from populated areas retain some material from space. Under a microscope, a micrometeorite may appear as a small rounded grain that once melted, or as a mineral fragment with a composition different from ordinary terrestrial dust. These particles expand our understanding of the continuous stream of material entering the atmosphere. They do not come from a single event, but from countless encounters occurring over long periods of time. Through them, scientists can study what kinds of dust commonly reach Earth, how the atmosphere transforms them, and how much cosmic material has been added to the planet over time. Even the material ablated from a meteor does not disappear completely. As the object's surface vaporizes, metal atoms such as iron, sodium, and magnesium become mixed into the upper atmosphere. Some remain within extremely thin layers of atoms that can be observed using instruments on the ground or carried through those regions of the atmosphere. As the vaporized material cools, it can condense into extremely small particles, commonly known as meteoric smoke. These particles are far smaller than any dust the human eye can see. They drift through the upper atmosphere, take part in chemical reactions, and are gradually transported downward through processes that unfold very slowly. The term meteoric smoke does not mean smoke in the familiar sense produced by a flame. It refers to collections of extremely small particles formed when vaporized cosmic material condenses again. Matter that was once part of a rock now exists as fine dust, dispersed across a broad region of the atmosphere. These particles can provide surfaces for other molecules to attach to. At very high altitudes, where temperatures can fall extremely low, water vapor sometimes freezes around the tiny particles and forms crystals. When enough of these crystals gather together, they can contribute to the formation of very high, thin clouds that are easiest to see after the sun has dropped below the horizon, but still illuminates them from beneath. These clouds are commonly called noctilucent clouds. They appear as bands of silvery or pale blue light in the upper atmosphere. Not every particle within them comes from meteors, and their formation also depends on temperature and the amount of water vapor present. But meteoric smoke can serve as tiny nuclei around which ice crystals begin to grow. Through this process, a piece of material that once traveled through space can become a very small part of an atmospheric phenomenon on Earth. It no longer retains the shape of a rock, but its matter continues participating in processes taking place above the planet. The atmosphere is therefore more than a place where incoming objects are destroyed. It is a region of transformation. Some of the rock becomes light, some becomes heat and pressure waves, some reaches the ground as meteorites, while other material continues to exist as metal atoms, micrometeorites, or microscopic dust within the air. The shield protects the surface, but it does not completely seal Earth away from outside material. It allows a small amount to pass through in transformed states. The larger surviving samples can be studied by humans, while smaller particles become mixed into the oceans, snow and ice, and the atmosphere. In this way, the planet is protected from most of the dangerous velocity of incoming material while continuing to receive natural samples from distant regions of the solar system. A meteorite in a laboratory can reveal the history of its parent asteroid. A particle of dust preserved in ice can record its passage through the atmosphere. A thin layer of metal atoms high above Earth may be the final trace of a meteor trail that faded long ago. The rock we have followed has completed its journey in both forms. The surviving fragment rests on the ground, preserving ancient minerals for humans to study. The material removed from its surface continues, drifting through the atmosphere in forms far too small to see. The atmosphere has transformed nearly everything that passed through it. But this natural shield only begins acting with full strength when an object is already extremely close, with only a few seconds remaining before the final stage of its journey. For dust and small rocks, those few seconds are usually enough. For a larger asteroid, the most effective protection cannot begin only at the edge of the atmosphere. It must begin earlier, while the object is still millions of kilometers from Earth, and there is enough time to detect it, track it, and gently alter its path before the atmosphere is forced to confront it. The most effective protection against a large asteroid cannot begin during the final few seconds, when the object has already reached the outermost layers of the atmosphere. It must begin much earlier, while the rock is still only a small point of light in space and remains far enough away for people to observe it, calculate its path, and choose an appropriate response. The atmosphere had been performing its work for an immense span of time before humans appeared. Every day, the thin layer of gas around Earth receives incoming dust, rocky particles, and small fragments of material. It slows them, heats them, erodes them, and breaks them apart. Most of these encounters end high above the surface, leaving no sound or clear trace on the ground. But this natural shield can respond only to objects that have already come close. It cannot see an asteroid years in advance. It cannot calculate an orbit, distinguish between an object that will safely pass by and one heading directly toward Earth, or deliberately alter the rock's path before the encounter begins. That task belongs to the next layer of protection, one built from observation, knowledge, and time. Across many regions of Earth, Tunguska continuously watch for meteor trails and fireballs. They record the direction, brightness, and timing of small objects entering the atmosphere. When several cameras observe the same event from different locations, scientists can reconstruct its three-dimensional path, estimate its speed, and sometimes trace the orbit it followed before meeting Earth. These observations do more than help search teams locate surviving meteorite fragments. Over time, they also reveal how often small objects enter the atmosphere, how large they tend to be, and the altitudes at which most of their energy is released. Every fireball becomes a natural measurement of how the atmospheric shield responds to material from space. Infrasound sensors add another part of the story that human eyes cannot see. When a large object enters and transfers energy into the air, low-frequency pressure waves can travel enormous distances. People cannot hear them, but specialized instruments can still detect their signatures, helping researchers estimate the location and scale of the event. Radar can track certain near-Earth objects with great precision. By transmitting radio signals and measuring the echoes that return, scientists can study an object's distance, rotation rate, approximate size, and sometimes even the shape of its surface. A tiny point of light seen through a telescope gradually becomes a physical object with motion and structure that can be studied. Ground-based telescopes search for points of light moving against the background of stars. They photograph the same region of sky repeatedly and compare the positions of objects over time. A distant asteroid may appear only as a faint dot, but its slight movement from one image to the next allows its orbit to be determined gradually. Observatories in space can help cover regions that are difficult for ground-based telescopes to monitor. Objects approaching from near the direction of the sun are especially difficult to see against the bright sky. Observations from different locations, or at suitable wavelengths, can expand our ability to detect dark rocks moving through the solar system. No single instrument can watch every direction at every moment. Planetary defense is therefore not built around one telescope, but around many networks sharing data. An observation made in one location is compared with measurements taken elsewhere. Orbits are updated as new information arrives. Initial uncertainties gradually narrow as an object is followed over many nights, months, or years. The purpose of this work is not to create the impression that danger is always nearby. Most detected objects will pass Earth at a safe distance. Tracking them helps distinguish ordinary close approaches from the few cases that genuinely require attention. A point of light may appear to be heading toward Earth simply because of the viewing angle. As more data is collected, the orbit usually becomes clearer, and the estimated probability of impact decreases. Science does not only search for danger, it also removes unnecessary concern through increasingly precise measurements. If a large object truly lies along a path that could intersect Earth, warning time becomes the most important resource. An asteroid does not necessarily need to be destroyed. In many cases, changing its speed by only a very small amount early enough would allow that difference to accumulate across millions of kilometers, causing the object to miss Earth when it reaches the point where their paths would otherwise cross. This is why planetary defense differs from the images commonly shown in movies, where humanity waits until the last moment and then uses an explosion to destroy the incoming body. Breaking apart a large object could produce many fragments continuing along difficult-to-predict trajectories. The safer objective is often to make a small change to its motion, while enough time still remains. One method being studied is kinetic impact. A spacecraft is sent toward the object and deliberately collides with it at high speed. The spacecraft does not need to be anywhere near the size of the asteroid. The impact only needs to transfer enough momentum to change the object's velocity by a small but measurable amount. The most effective protection against a large asteroid cannot begin during the final few seconds, when the object has already touched the outermost layers of the atmosphere. It must begin much earlier, while the rock is still only a small point of light in space, and remains far enough away for humanity to observe it, calculate its path, and choose an appropriate response. The atmosphere had been doing its work for an immense span of time before humans appeared. Every day, the thin layer of gas surrounding Earth receives incoming dust, rocky grains, and small fragments of material. It slows them, heats them, erodes them, and breaks them apart. Most of these encounters end high above the surface, leaving no sound or visible trace on the ground. But this natural shield can respond only to what has already come close. It cannot see an asteroid years in advance. It cannot calculate an orbit, distinguish between an object that will pass safely by and one heading directly toward Earth, or deliberately alter the rock's path before the encounter begins. That task belongs to the next layer of protection, one built from observation, knowledge, and time. Across many regions of Earth, all sky cameras continuously watch for meteor trails and fireballs. They record the direction, brightness, and timing of small objects entering the atmosphere. When several cameras observe the same event from different locations, scientists can reconstruct its three-dimensional path, estimate its velocity, and sometimes trace the orbit it followed before encountering Earth. These observations do more than help locate surviving meteorite fragments. Over time, they also reveal how frequently small objects enter the atmosphere, how large they tend to be, and the altitudes at which most of their energy is released. Every fireball becomes a natural measurement of how the atmospheric shield responds to material from space. Infrasound sensors add another part of the story that human eyes cannot see. When a large object enters the atmosphere and transfers energy into the air, low-frequency pressure waves can travel enormous distances. People cannot hear them, but specialized instruments can still detect their signatures, helping researchers estimate the location and scale of the event. Radar can track certain near-Earth objects with great precision. By transmitting radio signals and measuring the echoes that return, scientists can study an object's distance, rotation rate, approximate size, and sometimes even the shape of its surface. A tiny point of light seen through a telescope gradually becomes a physical object with motion and structure that can be studied. Ground-based telescopes search for points of light moving against the background of stars. They photograph the same region of sky repeatedly and compare the positions of objects over time. A distant asteroid may appear only as a faint dot, but its slight movement from one image to the next allows its orbit to be determined gradually. Space-based observatories can help cover regions that are difficult for ground-based telescopes to monitor. Objects approaching from near the direction of the sun are especially difficult to see against the bright sky. Observations from different locations or at suitable wavelengths can expand our ability to detect dark rocks moving through the solar system. No single instrument can watch every direction at every moment. Planetary defense is therefore not built around one telescope, but around many networks sharing data. An observation made in one place is compared with measurements taken elsewhere. Orbits are updated as new information arrives. Initial uncertainties gradually narrow as an object is followed over many nights, months, or years. The purpose of this work is not to create the impression that danger is always nearby. Most detected objects will pass Earth at a safe distance. Tracking them helps distinguish ordinary close approaches from the few cases that truly require attention. A point of light may appear to be heading toward Earth simply because of the viewing angle. As more data is collected, the orbit usually becomes clearer and the estimated probability of impact decreases. Science does not only search for danger, it also removes unnecessary concern through increasingly precise measurements. If a large object truly lies on a path that could intersect Earth, warning time becomes the most important resource. An asteroid does not necessarily need to be destroyed. In many cases, changing its velocity by only a very small amount, early enough, would allow that difference to accumulate across millions of kilometers, causing the object to miss Earth when it reaches the point where their paths would otherwise cross. This is why planetary defense differs from the images commonly shown in movies, where humanity waits until the last moment and then uses an explosion to destroy the incoming body. Breaking apart a large object could produce many fragments continuing along difficult-to-predict trajectories. The safer objective is often to make a small change to its motion, while enough time still remains. One method being studied is kinetic impact. A spacecraft is sent toward the object and deliberately collides with it at high speed. The spacecraft does not need to be anywhere near the size of the asteroid. The collision only needs to transfer enough momentum to change the object's velocity by a small but measurable amount. The DART mission turned that principle into a real-world test. A spacecraft was deliberately guided into Dimorphos, the small moon orbiting the asteroid Didymos. The goal was not to destroy Dimorphos, nor was it to save Earth from an approaching threat. That asteroid system was not on a collision course with our planet. The purpose was to test whether humanity could deliberately alter the motion of a small celestial body. After the impact, the time Dimorphos required to complete one orbit around Didymos changed noticeably. This showed that a planned intervention could shift an object's motion in a way that could be observed and measured. The collision did not immediately send the asteroid far away like an object knocked out of its path. The initial change was relatively small, but that is the central idea behind early planetary defense. When many years remain before a predicted encounter, a tiny deviation today can become an enormous separation in the future. Kinetic impact is not the only possible method, nor is it suitable for every object. A solid rock responds differently from a porous structure made of many smaller pieces. A rapidly rotating asteroid, an irregularly shaped body, or one with a moon must be studied carefully. Warning time, size, composition, and orbit all influence which method should be chosen. But the experiment delivered an important message. Humanity is not completely powerless against the motion of small objects in the solar system. We cannot control everything in space, but we can observe, understand the underlying laws, and apply a very small influence at the right moment. The deeper meaning lies not in the strength of the collision, but in the preparation that came before it. A small change becomes useful only when there is enough time for its effects to grow. Late detection makes every option more difficult. Early detection allows people to measure, test, and coordinate calmly instead of reacting only during the final seconds. This also reflects the way the atmosphere protects Earth. The shield does not defeat an object with one hard barrier. It works through countless small collisions, with each gas molecule carrying away part of the momentum, each layer of material being stripped from the surface, and each small amount of speed being transferred into the surrounding environment. Its strength does not lie in a single moment, but in accumulation. Planetary defense works in much the same way. One observation is not enough. A single telescope cannot protect an entire planet, but millions of images, years of tracking, orbital calculations, and cooperation among many research teams can create a layer of protection that nature alone never provided. It is not a new shell surrounding Earth. It is a shield made of information. The atmosphere is the first line of defense, natural and continuous. It does not need to be activated, and it requires no human control. Observational science becomes the next layer, allowing us to see what the natural shield cannot yet reach. Defensive technology, if it is ever truly needed, forms another layer farther outward, acting while an object is still distant enough for a small change to make a difference. These three layers of protection do not make Earth completely invulnerable. Nature will always be greater than humanity's ability to control it. But the existence of limits does not make every effort meaningless. Understanding those limits is the first step toward using what we have wisely. The atmosphere is not perfect, yet it has allowed life to exist beneath a continuous stream of cosmic material. Telescopes cannot see every object, but each year surveys add more newly measured orbits. One experiment cannot solve every possible situation, but it demonstrated that an idea once confined to models can work in real space. The lesson of the thin shield is not that Earth exists in constant danger. It shows that safety sometimes comes from layers of protection that are difficult to notice. Part of that protection was created by nature. Part comes from knowledge accumulated over generations. And part depends on whether humanity has enough patience to notice small changes before they become large problems. In life on the ground, the things that protect us often work in much the same way. A roof does not need to resist a storm every day to prove its value. An early warning may matter more than a powerful response after everything has come too close. A small change made at the right moment can sometimes be far more effective than a great effort that arrives too late. The universe does not offer lessons in the way people usually tell stories. It simply follows consistent laws. But by observing those laws, we can recognize the value of preparation, cooperation, and humility. Not everything can be stopped through force. Often, what matters more is seeing early, understanding correctly, and shifting just enough. Above the observatories, small objects continue orbiting the Sunday. Most will never come close to Earth. Some pass at great distances. Others eventually encounter the atmosphere and appear for only a few seconds as a streak of light. The rock that has accompanied us through this entire journey is also reaching its final stage. Long before this moment, it once rested inside a larger celestial body. A collision released it into space. Sunlight and the gravity of the planet slowly altered its orbit until its path crossed Earth's. As the blue planet grew larger ahead, the rock saw no wall. It simply entered a region where gas molecules were separated by great distances. The first collisions were too rare to produce light, but every kilometer of descent brought more air into its path. A region of compressed gas formed ahead of it. The temperature rose. Atoms absorbed energy and began to glow. The surface that had remained cold and dark in space lost its first layers, leaving a brief trail of light behind. The rock grew smaller. Its fractures widened. One solid body divided into several pieces, and those fragments continued to undergo ablation as the atmosphere removed their speed. Within only a few seconds, a journey lasting millions of years became light, heat, and a thin wake of turbulence in the upper atmosphere. No sound reached the ground. No windows shook. No crater appeared in a forest or ocean. The people living below continued working, brought a long day to an end, or slept peacefully without knowing that material from space had just passed overhead. Part of the rock became metallic vapor. Atoms that had once rested within ancient minerals mixed into the upper atmosphere. As they cooled, some of the material condensed into particles too small to see, continuing to drift within the layer of gas the rock had once entered at tremendous speed. Some particles may remain high above for a long time. Others gradually descend and mix with the dust of Earth. Perhaps a tiny portion eventually settles into the ocean, resting among countless other mineral grains and never being recognized. The object no longer exists as a stone, but its material has not disappeared. It has simply changed form and become part of the planet that prevented it from traveling farther. The atmosphere does not stop the universe from touching Earth, nor does it separate the planet from the rest of the solar system. Instead, these exchanges continue every day. Dust enters, atoms mix into the air, micrometeorites settle into the sea, and rare fragments of rock reach laboratories. The shield does not close the door. It softens what passes through. Viewed from far away, Earth is still surrounded by an extremely thin blue outline. Beyond that boundary lies the vastness of space, where countless fragments of material continue moving along different orbits. Below it are clouds, oceans, continents, and ecosystems that have developed beneath the protection of this fragile layer of gas. The distance between space and life is not marked by a thick wall. It is only a region of air that gradually thins across hundreds of kilometers, held in place by the planet's gravity. Yet within that narrow region, speed can become light, rock can become dust, and an impact can be softened before reaching the ground. Perhaps that is the deepest meaning of this shield. Protection does not always appear powerful. It can be thin, almost invisible, revealing its strength only when something attempts to pass through it. It does not eliminate every danger, but it reduces most of what could cause harm. And when its limits appear, knowledge allows humanity to continue the work. Below, life does not need to feel every particle of dust being stopped high above. Trees continue moving in the wind. Waves continue reaching the shore. Cities light up and then grow quiet as night arrives. And above everything, the shield that appears so fragile continues its work, second after second, day after day, needing neither to be seen nor ever truly resting.